This conference will now be recorded.
So, hello one and everyone joined in our today's webinar. A very good morning, afternoon, and evening to everyone present here. So, I will introduce myself. This is Emma. So, today's organizer. If you have any queries, you can just let us know. I will be there to help you out. So, as some of them are new today, so I will just once go through the tools and procedure for this GoToMeetings app. Now, as the attendees have new to, I can explain you the important settings. As you have joined through the link provided, you can see the screen where you can find four icons at the bottom of the center of your screen. First one is mic. Click on that to mute or unmute yourself. So I request you all to stay muted while our speakers are presenting their research work so that it doesn't cause any disturbance to them. Camera, you can use this button to share or unshare the webcam. If you have the option, you share the webcam or it's completely your choice. Third one is screen. You can use this button to share your screen at your schedule. When I will call your name from my side, I will be making you the presenter. When I will give you the access to share you the screen, then you need to click on this button and you will find a pop-up window which asks you to share the screen and you can proceed further. For MacBook and Apple device users, once I make you the presenter, then you need to give permission to share the screen in your system preferences. After that, you need to log out from the session and need to join again from the same link and share screen for the presentation. Leave, this is your fourth icon that when the last clicking on this button will leave you from the session. On the top right corner, you can find four icons. First one is people, which show you all the attendees of the conference. Second one is chat. In this option, you can chat with me or any other participants for any queries or questions. Third one is notes, where you can write down your notes. Fourth one is settings. You can use this button to check for the settings for your speaker and microphone. So as mentioned, kindly remain muted during the presentation so that the presenters don't get disturbed. And for any questions, you can ask me or can write in the message box too. Finally, I would like to request you all to give a brief introduction about yourself before starting with the session so that we can know about you virtually. Now let's move on to the session. So our first is the keynote presentation from Dr. Sukhdev Roy from Dayal Bagh Educational Institute, India. And the title of the talk is Controlling the Brain and Heart with Light. So hello, Dr. Sukhdev.
Yeah, hello everybody.
Yeah,
Thank
hi.
you very
You
much.
are the
Yeah,
presenter now. Please click on the share icon.
yeah. It says screen sharing requires permission to capture your screen. Please open system preferences to
Yes,
grant
yes.
permission.
Yeah, are you using the MacBook?
Yeah, I'm using a MacBook Air.
Yeah, yeah. Then you need to go to the system preferences and you need to give the permission. After that, you need to log out from the session and again you have to log in from the same link. Then it will work.
So, so I have to log out and then, reopen it.
Yes, 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 yes.
Reopen what?
You have the link, right? You can join from the
Yeah.
same link.
Okay, okay, okay. So I have to leave
Yes,
first, huh?
yes, yes. You have to leave. Yes, now you can share the screen. Yes. Yes, perfect. We can able to see your screen. You can make it a full screen.
Yeah.
Perfect. Please continue.
Okay. So thank you very much. It's a pleasure and honor to deliver this keynote address in this conference. I am Sukhdev Roy. I am a professor and head of the Department of Physics and Computer Science at the Dayalbagh Educational Institute, which is located in Dayalbagh, Agra, the city of the famous Taj Mahal in India, in the heart of India, in northern parts of India. And this Dayalbagh Educational Institute is a very unique institute, a university where I work, and it has a very innovative education system and very dynamic environment for teaching as well as research. So I obtained my PhD from the Indian Institute of Technology, Delhi in 1993 and joined this department ever since. So I've been here for the past 30 years. I My area of research are at the moment I work in photonics and specifically in silicon photonics, biophotonics, nanophotonics, and the recent interest has gone into neurophotonics. So, how can you control the brain and heart with light? So, something which is very fascinating, and we've been looking into also other aspects of neuromorphic computing. And I had been the guest editor of the special issue on optical computing of the journal Circuits, Devices and Systems, IET Circuits, Devices and Systems in 2011. And I have published about 11 book chapters and about 175 publications in journals as well as conference proceedings. I have been a visiting professor at Harvard, University of Waterloo in Canada, University of Würzburg in Germany, City University, University of London, Queensberry University of London, and many other universities, Osaka University in Japan, and the Royal Institute of Technology, Stockholm. So, with these words, let me begin the presentation. So, the title of the presentation, as you can see, is Controlling the Brain and Heart with Light. Now, the outline of my presentation would be the following. I would first focus on the importance of optogenetics, a new area which has revolutionized neuroscience. What are the challenges and what is the importance of computational optogenetics? And then I would focus on our recent results on optogenetic switching of neurons that involves excitation of neurons, inhibition of excited neurons, and bidirectional control, both excitation and inhibition that can be done. Then we have made a very important application of this to retinal prosthesis. How can you cure blindness? And then one, I would focus on another very novel method that we have proposed, and that is to overcome the fundamental limitation of optogenetics, and that is to have long-term high-fidelity excitation using light. And then I would also take you to through an overview of cardiac optogenetics and our recent research results on low-power, deep, high-fidelity control of of cardiac cells within the heart, and then finally make a conclusion. Now, you see, the brain is the most complex system in the known universe. And how do you decode the brain? You look at this a pulpy system, all right, which has about 100 billion neurons, each has 10,000 connections, and the brain network is so complicated, it is over 1,000 trillion connections. We get as many as 70,000 thoughts a day. Where do they come from? How does this system process? How does it work? So we need to understand its architecture, function, signal processing, and can we control the system through a non-invasive, non-intrusive, highly precision mode where one can control a single neuron, all right, and then see what is the functionality of a single neuron in this entire 100 billion system of neurons with high efficiency, fast control, and also through a cost effective measure. Now, this century is being claimed to be the century of the brain because we need to understand who we are, how do we function, all right, and how do we how do we understand health and well-being? Okay, so this is the central nervous system, the brain. Now we have why are we optimistic of of understanding the brain now? Because we have very advanced neuroimaging techniques such as the functional magnetic resonance imaging. Now, if we look at uh, this slide, we find that there are clusters of neurons which get activated when you perform certain functions, such as listening, seeing, or combining both listening and seeing. Now, the problem is that these cluster of neurons have large number of neurons, and we do not know what is the functionality of a single neuron. All right, and this is through measurement of the bold signal, blood oxygen level detection, because when you perform certain functions, the blood flows into those neurons, and then you try to measure the very fine magnetic fields that are generated, or the electric currents that are created when the signal gets processed here in these different parts of the brain. So the point is, we need very high spatio-temporal resolution, and these techniques still are lacking in this aspect. So there have been tremendous global initiatives on brain research ever since 2013. So 10 years have already passed through. You have the Human Brain Project, European 1 billion already committed to this through the European Commission, Obama Initiative, the Brain Initiative, Human Connectome Project, the Swiss Initiative, that is the Blue Brain Project, and so on and so forth. Now, in a very ingenious technique, people proposed in 2002, 2005. In fact, before that, in 2002, channel rhodopsin was discovered by a group at the Max Planck Institute for Biophysics in Germany. And they actually found a rhodopsin which actually is sensitive to light, and when you shine light, it opens a channel and allows ions to conduct through that channel. Now, a group at Stanford led by Carl Dizereth, they thought that why not integrate these channel rhodopsins into neurons and see what happens, because when the neurons have these channel rhodopsins and you shine pulses of light on these neurons, these channels are going to open and they would allow ions to conduct, and so therefore a synapse can be triggered. And this actually won the Brain Prize in 2013, and this was has created a massive revolution in neuroscience. And six of these eminent scientists shared the Brain Prize in 2013. Now, this is what happens. You have, let's say, an organism such as Chlamydomonas renati. You have this photosensitive protein which you take through a vector, and then you put it genetically, encode the neuron with this vector such that these channel rhodopsins go along with the neurons on the surface, and when you shine, let's say, blue pulses of light, they open up and allow ions to conduct and a synapse to trigger in the neuron. Now, optogenetics, therefore, is a system which can also be used to cure blindness. So, for example, photoreceptor cells are lost due to aging and macular degeneration. So, can you plant these channel rhodopsins and treat the blind mice? So you can see this animal is trying to find its way through the maze, but a treated mice immediately sees the outlet and is able to go out of this maze. Now, similarly, you have, at different parts of the brain, you can then have these neurons having these channel rhodopsins, and you can have a fiber optic cable through an electrode. You can shine pulses of light and see how it behaves. So, this is an overfed mouse which does not require to eat. But the moment you do not have a light triggering those neurons, it does not eat at all. But the moment a pulse of light, a blue pulse of light through the fiber optic cable comes in, it starts eating. So people claim that they have identified neurons responsible for overeating. All right. So you therefore study different aspects of behavioral aspects and then see how an animal behaves under certain conditions. Now, a major limitation in this case is that the length of the fiber cable restricts the movement of the animal. So, it would be good if one can have freely moving animals, and so therefore you have even wireless optogenetics that has come about. So, you can have an electrode implanted on the head or the brain of this animal, and it can be self-powered as well. And so, therefore, you can use a remote, all right, and then control its behavior over a larger distance. So you have nanobiophoton. So integration of three major thrust areas, modern age thrust areas, which get into optogenetics, one important objective is to cure neurological disorders. The other is the capability to enhance performance. All right. So this is the electrode, how small it is, and there's a comparison between optic and electronic. You can see the tremendous advantage in terms of the weight, and here you find uh, an animal, a subject being controlled remotely, all right, through wireless optogenetics. So the fact of the matter is that there are different kinds of channel rhodopsins that have been discovered, and their genetic mutants have been studied over the years, and people have tried to even tailor the response of these photo response of these channel rhodopsins so that one can achieve the desired objectives in practical applications. So here you can see that you have excitation. So there are different what to say, rhodopsin proteins that have been discovered or tailored through genetic engineering, where they go into different spectral regions, and also the kinetics are different, so that you have here light off. When the light comes in, a blue pulse comes in, the conduction takes place and the neurons start firing. Similarly, if you have neurons which are firing and you have an opsin such as an opsin which is sensitive to orange light, when as soon as the pulse comes in, the spikes disappear, and so therefore inhibition takes place. On the other hand, you can have uh, two opsins which can be co-expressed, and so therefore using different pairs of opsins, people have shown that you can switch on and switch off the neuronal switching, and so therefore you can study anxiety, Parkinson's disease, auditory system, memory deficits, and so on and so forth, and see how best one can find a cure to these major problems. Now the challenges in optogenetics is that we want to have low power control, as low as possible, high frequency control, temporally precise control, so that suppose I want to inhibit, let's say, the uh, spike number 47, then I should be able to inhibit that particular spike at that moment of time. Then we need minimizing heating effects. So whatever be the case, we do not want to damage the tissue or the neurons or the brain. So low power and would also ensure minimizing heating effects. Then we want deep penetration of light. So as you know that blue light gets scattered most. So therefore, there is a focus on trying to have red shifted options so that you can have deeper penetration of light. We need independent population control. So people have used holographic techniques or patterns, forming patterns to excite or control different clusters or different neurons in different parts of the brain. Now, testing these different options, their combinations and photostimulation conditions is very, very challenging. And experimentally, you cannot test all these different kinds of options and photostimulation conditions, permutations, and combinations, and then optimize it to achieve these higher objectives. So therefore, computational optogenetics becomes very, very important and significant. So if I can have accurate theoretical models, then I can predict what would happen under certain conditions with different options and so on and so forth. Now, in computational optogenetics, what are the major aspects that one has to look into? So, theoretical modeling involves modeling the photocurrent of the opsins first, okay, and then integrate it into the neuron model, and then try to see how the neuron would respond, all right, theoretically, and then validate it with the experimental results that have been reported. So there can be different kinds of intermediate states, the photocycle which the opsins exhibit, and so therefore one has to take into account as many factors as possible so that one can accurately explain the experimental results. So for example, CHR2, this is channel rhodopsin 2, and Chronos, a recently discovered opsin. So they can be very accurately modeled with a four-state model. So these are the rate equations, these are the parameters which one can extract from the experiments that have been reported. Similarly, for the inhibitors, you have the natronopheronis, halorhodopsin, and JAWS. Okay, and one can also include other effects such as blue light activation, chloride rebound effect, and so on and so forth. And so, therefore, generate different kinds of models. Then there are different kinds of neurons in the brain. So you have, for example, hippocampal neurons, or you have fast interneurons. So one has to first validate the theory with the experiments that have been reported in the literature, and people have been working on hippocampal neurons and what to say, different kinds of neurons, but prominently hippocampal neurons and fast interneurons and retinal ganglion neurons. So these are the gating function parameters of ion channels that have to be taken into account in the theoretical simulations, theoretical model. So these are Heman neuron model parameters, all right, gating function parameters for the Wang-Buzaki neuron circuit model, interneuron parameters, and so therefore then one can formulate a theoretical model. So first modeling the photoresponse of the opsins and then integrating it with the neuron circuit model to have a comprehensive model for optogenetics. Now in 2014 in Nature Methods, a group at MIT discovered a new opsin which is called Chronos. Okay, it has a very high photocurrent, high light sensitivity in the region, blue-green region of the spectrum, fastest reported kinetics to date with an on-off time of 2.3 and 3.6 milliseconds. It has shows 100% spiking as at intensities which are very very low, such as 0.05 milliwatt per millimeter square to 20 milliwatt per millimeter square, and you can control the neural spiking across a range of expression levels. So we formulated a theoretical model for Chronos, taking into account these different factors, and this is the comparison between experiment and theory. So you can see for 5 milliwatt per millimeter square, Chronos shows excitation from 10 hertz to 60 hertz high frequency, and this is the experiment which was reported in the literature, and this is the theory. So you can see the theory is in very good agreement with the experimentally reported results, and from theoretical simulations one can even see what would happen if you have 2 milliwatt per millimeter square at less intensity. So 40 pulses with 2 millisecond pulse width at 530 nanometers, this is the neuronal spiking response that you can see. Similarly, here we have the comparison between CHR2 and Chronos. Okay, comparison between experiment and theory. So experimentally, it had been reported that at zero point 0.1 milliwatt per millimeter square, CHR2 is not able to generate constant spiking, whereas Chronos, which is very sensitive, even at these small light intensities, it is able to have a very what was a stable output. Okay, so this is again theory which you can see is in excellent agreement with the experiment. So with this one can then optimize and see what is the effect of conductance and pulse width. So as you can see here, as you increase the conductance, you find that there are multiple spiking, burst spiking which takes place. Similarly, when you increase the pulse width also, you have spiking, multiple spikings that take place. Similarly, the effect of the stimulation rate, you can see that you have pulses at 473 nanometers here, and you can see that Chronos has driven rate which is as high as 280, all right, spikes per second, which is very high compared to CHR2. Now, these results were reported in Neurophotonics in this issue in 2018, and all those who are interested can look up this paper and find more results. Now, in 2018, a group at the Max Planck Institute for Biophysics in Germany, they discovered a red-shifted opsin, and this is what is called very fast crimson. So we again prepared a theoretical model using the experimental parameters reported in the literature. You can see the comparison between experiment and theory, which is in very, very good agreement. And using these, then one can find out the optimized values of how high a frequency can you go if you use this very high frequency, high crimson, opsin mutant. So here you can see that in with these parameters, delta t 0.5 milliseconds, intensity 10 milliwatt per millimeter square at 565 nanometers. Okay, with this, I mean, these parameters, you can go to as high as 1 kilohertz, and these neurons can respond to those high frequency values. Similarly, here for the inhibition, you can see experiment and theory. So as soon as this pulse comes in, it inhibits the the neuronal spiking. This is again another comparison between experiment and theory. So we are able to very accurately model, which is very very important. All right, contribution such that one can then look at how can one optimize and find out the best possible combination of photostimulation and opsins so that the experimentalist can then achieve better results. So here we have NPHR 3.0 and JAWS, and you can see that you can go to 160 hertz and as high as 250 hertz, all right, inhibition at very high frequencies. Now, these are some of the pairs that have been reported in the literature for bidirectional control. So these are control of locomotion. They have studied anxiety, memory deficits, auditory system, Parkinson's disease, and so on and so forth. Now, there are many recently discovered options that have not yet been studied. So there are excitatory options like soul, CHR9, Crimson, and so on. There are inhibitory options which are shown in the slide with the references alongside. And what we therefore uh, tried to do was first develop theoretical models for these experimentally studied option pairs, find the optimized conditions, and then study new prospective option pairs and see can they add value to the existing study. So here is again a comparison between experiment and theory. So the first step is to validate the theoretical model and then go to optimization. So you have hippocampal neurons which can go up to 60 hertz, neocortical neurons which can go up to 100 hertz with the combination of CHR2 and PHR. But if you take new option pair, you can go up to 90 hertz and 180 hertz. All right, in these hippocampal and neocortical interneurons. Again, you can go to 90 and 250 hertz with Chronos and ENPHR 3.0. So these results were reported in Neuroscience in 2020, and one can look up this reference for further details. Now, retinal degenerative diseases again are very, very important. Loss of function of photoreceptors actually then makes a person blind, and there are retinitis pigmentosa or age-related macular degeneration. There are different techniques, but there you can probably look into retinal prosthesis where indirectly you can generate an electric signal to remaining excitable cells. Now, you look into the non-invasive and spatial resolution of these different techniques that have been used, and optogenetics has very high spatial resolution, all right, along with non-invasiveness, so that it becomes a very prospective technique. So here in 2021 in Nature Medicine, the first human trial was reported, and they showed that partial recovery of visual function could be possible in a blind patient after optogenetic therapy. So what they did was they took these goggles and used Crimson R option, all right, and they showed that they were able to partially recover the vision of a visually impaired patient, human patient. Now, in, in Science in 2019, a new option was reported, which is called CHR Mine by Carl Deseret's group at Stanford. And it is a redshifted CHR mine, large photocurrent, high sensitivity, fast turnoff, and fast recovery kinetics. So we thought, why not look into the application of CHR mine for retinal prosthesis? So this has not been studied to date, and it has very significant features, all right, which would be helpful. So here you can see the effect of pulse to pulse irradiance change. And as you can see that at very low intensities, 10 to the power minus 4 milliwatt per millimeter square, CHR mine triggers neurons, whereas none of the other options which are there in the literature or have been studied in the literature are able to do so. So CHR mine expressing retinal ganglion neurons begin to respond at 2 orders of magnitude less intensities compared to Crimson R. Similarly, CHR mine expressing RGNs fire up to 280 Hz at 10 to the power minus 2 milliwatt per millimeter square. Similarly, you have an order of magnitude shorter first spike latency in CHR mine expressing RGNs and stable latency of subsequent spikes in CHR mine expressing RGNs. As you can see, the constant red line, all right, on the right graph. Similarly, you can have high frequency control, but CHR mine expressing RGNs go up to 40 Hz, although irradiance is 2 orders lower than safety threshold, but Crimson R expressing RGNs can go up to 100 Hz with irradiance which is above the safety threshold, so which is not advisable to use in practical human subjects. So this is the comparison, and you can see that CHR mine can operate at 0.6 microwatt per millimeter square and 280 hertz maximum firing frequency and so on and so forth. So this study is very important for low power and high frequency optogenetic retinal processes, and this was reported in published in Journal of Neural Engineering in 2021, and it has already 1057 downloads up to March 14, 2023. Now, this slide shows various light sensitive proteins which have been used in optogenetics. So there are blue sensitive, red shifted, ultra fast, excitatory, inhibitory, and biochemical. Now, one important thing is that for ultra fast options, you need very fast kinetics, but they are poor light sensitive. Light sensitivity is very poor because of fast desensitization. Spike failure takes place under sustained light. All right. So spike failure due to photocurrent desensitization is a major issue in optogenetics. Now, on the other hand, there is a class of opsins which are called step function opsins. They have very slow kinetics but very high light sensitivity and a faster switch off at another wavelength, but small photocurrent. The idea is, can we so there is a need for long-term high-fidelity excitation with short-term plasticity, homeostatic plasticity, urinary bladder dysfunction, neuroprosthetic circuits, cardiac pacing, etc. And so there is advantage for of fast channel rhodopsin and bistable opsins, and they also have their limitations. So we were motivated to look into this hypothesis that can we solve this major problem of low power, high frequency, long sustained excitation or control of neurons with light by co-expressing a fast channel rhodopsin with bistable opsins in the same neuron. All right. And a theoretical study, therefore, was carried out where we looked into new combination of fast CHR2 plus SF4, various combinations with cheetah, which is fast opsin. So we formulated a computational model which took into account these two options and their different models, states, intermediate states in the photocycle, integrated with the neuronal models. These are the parameters, gating functions, and then one has to see validate the theoretical model, and you can see there is very good agreement between theory and experiment under these different conditions. And one can then therefore look at normalized photocurrent under pulse excitation and corresponding variation of membrane potential with time. So here, therefore, from these graphs, one can see that you can have non-invasive deeper excitation using these different pairs of, this what to say mutants of opsins, and you can go to tissue depth from 7.1 millimeter to 9.1 millimeter. So by using these combinations and the wavelengths, you can go deeper. Similarly, there is a problem of spike bursting. All right, but you can control it with red shifted light. So you have here blue light pulses and red shifted light pulses. So whenever the red shifted light pulse comes in, you find that this bursting can be removed. So at different intervals, using this combination of these options, one can burst control with red shifted light. Similarly, one can have high frequency, high fidelity limit, and this is a comparison with these different pairs of what to say um, options that we have studied, and you can see that upper and lower frequencies indicate the spiking and stimulation frequencies, and one can therefore see what would be the best combination, all right, which would give us high frequency, high fidelity limit. So these results were published in Journal of Neural Engineering in 2022, and if people are interested, those who are interested can study this very interesting, important paper and find more results. Now, if you look at the causes of death, you find that cardiovascular diseases are the major contributors to the death causes of death. All right, compared to other ailments, and there are different types of heart disorders. Now, controlling the heart with light, can it be possible? There could be different, there are limitations of the electrical treatment in terms of high voltage shock, myocardial tissue damage, and so on and so forth. But there have been reports where people have tried to look at light beams, not pacemakers, could be the future of heart treatment. And can you, treat first human heart cells with pacing with light, or you have an optical pacemaker, all right, so on and so forth. So the advantages would be cell type specificity, shock-free excitation, pain-free stimulation, no tissue damage, bidirectional control, and so therefore cardiac optogenetics from neural optogenetics, people have progressed to cardiac optogenetics where there are so many applications that have emerged, all right, out of this ideology. So you have subcellular scale, you have cellular scale, tissue scale, and organ scale. So from angstroms to centimeters, one can therefore one can study experimentally and also theoretically through computational optogenetics how would the heart respond or the cells respond with excitation with light. So there are current challenges in cardiac optogenetics. Again, low power, non-invasive control, long-term excitation, large volume excitation, high frequency control, and temporally precise control. So this is the theoretical model that we have formulated recently, taking human ventricular cardiac cells into account, the different ions that are passed through the membrane, photocycle model of CHR mine, the recently discovered opsin, and then integrated it into a biophysical circuit model of CHR mine expressing HVCMs. So to get the a very comprehensive model, all right, that takes into account all these factors. So this is the theoretical model, the different equations, the gating function parameters for ion channels, intent to show cardiac cell circuit model, the human ventricular cells, and so on. And even taken, we have taken into account the light attenuation in cardiac tissue as it goes into the depths of the heart. And you can see that our reported results, theoretical simulations, are in very good agreement with reported experimental results in the literature. Similarly, so again, we have then looked into the effect of different photostimulation conditions. So, what would be the effect of irradiance? All right, as you increase the irradiance, you can see that action potential is activated after a threshold irradiance. And similarly, for CHR mine expressing HVCMs, the effect of pulse width is such that there is no change in action potential duration up to 100 milliseconds, and minimum irradiance threshold decreases with increase in pulse width. So optical pacing at high frequency can be done, but when you are talking about heart, high frequency range is from in hertz. Okay, so 2 hertz you can see that you can control and you can have a very stable optical pacing, and single spike resolution is maintained up to 2 hertz with 60 at 650 nanometers, 20 millisecond pulses, and 0.18 milliwatt per millimeter square. Similarly, light attenuation in cardiac tissue is a function of wavelengths, and you can see how the intensity varies with actual distance. And for deep excitation with CHR mine, we need to have redshifted opsin, which is CHR mine. And here, if you show, we show that low power optical pacing is possible at 1.5 hertz with at zero point 0.7 microwatt per millimeter square. And deeply situated CHR mine expressing HVCMs can be safely excited up to 10.2 millimeters, which is an increase of 2 millimeters, all right, which was reported earlier in the literature. So to conclude, we have formulated accurate theoretical models for the photoresponse of opsins. These are the various opsins that we have studied, the more prominent ones. Then we have studied the optogenetic control of opsin expressing neurons, excitation, inhibition, and both excitation and inhibition, which is called bidirectional control. Then we have studied hippocampal neurons and fast in spiking interneurons, HVCMs, and retinal ganglion neurons, because these are the studies that have been reported in the literature, and we need to validate our theoretical models with the experiments. And then we have gone further and undertaken optimization with both continuous and pulse stimulation to achieve low power, high frequency, temporally precise, and deeper control of neurons and cells within the heart. So this analysis is useful for engineering the properties of opsins. So you can tailor the opsins so that one can get these desired properties to design new optogenetic experiments with higher spatiotemporal precision or resolution. These models can be easily integrated to different types of cardiac cells, such as Atwill cells and Purkinje cells. You have fast, cost-effective method to optimize photostimulation conditions, and then you get new insights about the complex mechanisms, and we need to address the challenge of understanding neural coding. How does neural signal processing takes place between different neurons? What is that language? What is that coding? And finally, this study helps in design of compact, low-cost, durable, implantable optogenetic devices such as optogenetic cardiac pacemakers with reduced size and enhanced battery life. So if they are very sensitive and they are operating at very low power intensity level, then they would enhance the battery life further. So I would like to acknowledge my PhD students who have been working in this area, the funding agencies, UGC, Department of Science and Technology, and the Dalbag Educational Institute, my parent institute, for their full support. Thank you very much for your kind attention. And if there are any questions, I would be very happy to answer them. Thank you. Hello.
Thank you, Dr. Sukhdev, for your presentation. So, any questions from anyone? No questions then. Thank you once again for your presence and presentation.
Thank you very much, ma'am. Thank
Thank
you.
you. So our next presenter is Dr. Alien Zezat from University of Bamenda, Cameroon, and the title of the talk is Self-Trapped Moving Cavities Solitons, Solution of the 2 plus 1 dimensional cubic quinti-complex Ginzburg-Landau equation. Hello, Dr. Alien.
Yes, hello, madam. Good morning.
Yeah, hi. Yes, I'm going to make you the presenter. Please click on your share icon that is on your screen,
Yes, madam.
and please, your voice is very low. Please speak louder.
Thank you. Good to understand. Do you understand me very well?
Hello.
Hello?
Yes, yes, it is audible.
Okay.
Yes, we can able to see your screen also.
Please make it.
Hello, Dr. Alien.
Yes, madam. Hello.
Yeah, can you please
Okay.
start from the beginning?
Okay, madam.
Yes.
Thank you, madam. Yeah. Thank you, madam. Thank you, dear member of the panel. I'm Dr. Jazet. I said, madam. I'm from the University of Bamenda, Cameroon.
Can you please
Department of.
speak a bit louder?
Okay. Thank you. I am Dr. Jazet Alain
Yes.
from the University of Bamenda, Cameroon, Department of Petroleum Engineering, National Polytechnic Institute. Yeah. Our presentation is entitled Self-Trap Moving Cavity Soliton Solution of the Coupled Please 2 plus 1 dimensional cubic kinti complex Gizbolando equation. Our presentation is focused on the laser cavity soliton. In fact, during the past decade, many work have been done in the access of laser. And today, we have advanced evolution in the area of optics, particularly in the area of medicine, research, and also in the military. For this presentation, we are doing as follows. We are going to start with the introduction. In two, we are going to present the Maxwell block modeled the interaction between electrofield and matter and the tonsorial nonlinear polarization that we have derived. The vectorial 3 plus 1D cubic complex Gilbolando equation and the analytical treatment will be subject of the part 3. In 4, we are going to present our result and discuss and finish with the conclusion. Today, madam, as you can see in this slide, we see that the information is the main idea that you have to treat. As we are thinking, as we are speaking now, I'm far away from Cameroon, and you are in Prairie because the advance of the research. Also, recently, you understood the American military said that they are now able to make the war with the laser. It means that laser have is a good tool for the incoming world of science. Science, yeah. You can also see the treatment of cancer and the application in the industry. Nevertheless, the research in science have been much progressed, but encompass some problem. It is why we need to improve uh, our research to know the impact of the higher order nonlinearity on the existed model describing the propagation of the laser field. As an objective, you have to present the understanding, you have to present our understanding on the physical process involved the higher order nonlinearity in the laser cavity model. Thereafter, study the stability condition of the multidimensional dissipative soliton based on the soliton trap at the bottom of the effective potential well. Let us remind that the stability of the multidimensional soliton is very important. And also in dissipative system, we know that we have the localized solution, not the familiar solution as in the conservative system. The laser generally is composed of very component, and inside we have a material that can describe by it the level of energy as shown in figure 2 in this light. But for each material, we just have two level of energy where we can have the laser phenomena. The main equation that can describe the interaction of the material with electric field is the Maxwell block equation give by the set equation 1 to C, where the first, it means equation 1a, describe the propagation of electric field into material. B, the evolution of the polarization, and D, the variation of the density of population, of the difference of population. In the beginning of 1919, Jules Leger considered that as the system is composed of the many components, therefore it consider the vectorial form of electric field, and then first derive the cubic complex Gibbs-Burlando equation. Then that model show many good results, such as it helped to describe the topology, the generation of certain pattern, such as the default topological pattern. But that model cannot describe very well the stable dynamic. In fact, in order to have the stable dynamic in the dissipative system, we used to have the cross compensation between the loss and gain, also the diffraction and nonlinearity. That is why we try to analyze the influence of the higher order nonlinearity in the system. Thereafter, in the beginning of the year 202, in the past last decade, yes, some researchers showing that there are some technique to analyze the effect of the higher nonlinearity in the Maxwell block system. That technique is focused on the study on each component of the electric field, polarization and density of polarization as given in equation in the state equation 2, A, B to C and C. Using those equations of relation 2, we have derived from the Maxwell block the tensorial nonlinear polarization given by relation 3. That our nonlinear polarization have 3 components and describe the third harmonic generation. The first uh, the first term of our polarization describes the third harmonic generation, and it can be implemented experimentally with the technique of resonance. So as technique of resonance, we have today the electromagnetic transparency technique. That is a very good tool in laser science and a quantum mechanics science. In fact, today we have a many work on the quantum computer. When talking on the quantum computer, we also know that we cannot talk about quantum without the storage system. That electromagnetic transparency method helped to analyze the efficiency and the storage of the quantum storage. The second term of our polarization showing to be different to the other two one. In fact, we think that it propagates in the opposite direction with the other and describe the resonance of on one photon, whether the last term of our polarization we have the same direction with the electric field describe the resonance at 2 photons. We have in figure 3 and 4 different case of a third harmonic generation, where in figure 3a we have the third harmonic generation with 3 virtual level of energy, and in B we have energy level of real atom. Figure 4 present resonant at 1 photon, 4b resonant at 2 photon, and figure 4c the resonant at 3 photon. For more explanation, we can consult the book written by Robert and all and published in 1803 at Optical Academy. Thereafter, using our derived nonlinear polarization and apply the technique of nonlinear perturbation precedently used by Gilles Leger, we derive the vectorial model of the Gies-Bulando with 2 additional terms that describe the kinetic, the tensorial kinetic nonlinear term. Here we can see clearly that the term with coefficient C5 correspond to the second and the third term of our nonlinear polarization. it means that they are induced by the um, by the generation of the third harmonic, the transition of the resonant at one photon and at two photon. Yes. The last term with coefficient say 6 correspond is induced by the polarization, the first term of our nonlinear polarization, that is induced by the generation of third harmonic. Taking into account that our polarization is not linear, we consider that our vectorial electric field can be expressed in the form given by equation 5. Introducing equation 5 into equation 4, we obtained our new model with the cubic nonlinearity and the kinetic cross term given by delta I. In the case of the cubic cross term, we have two, the simple kinetic couplet and the mixture of kinetic couplet. You know that our aim is to analyze the stable solutions of this model. That is a good tool for optics and technology. So, to do well, as our model is not analytically treatable thoroughly, some approaches exist to analyze the solution of such system. In this work, we focus on the variational approximation method. That model have the advantage to display the impact of our system on the solution during the propagation. Taking the moving to taking at taking our solution as a symmetric Gaussian moving Gaussian ansatz solution given by relation 6a, we obtain the relation 6b to f, and we see that amplitude, the dynamic of amplitude, ledger, width, shape, and the central position, and the moving position depend on the parameter of our assumed solution, and also on the parameter of our solution of our system. Let's just remind that the parameter of our system talking about is the dimensionless parameter. Yeah. In order to study the stability of our solution, we recently see that on the work doing by Njoko and all, that it is possible when we have the variational equation of our system, we can derive the resulting effective potential from the relation 7 of our script. After deriving the expression of our effective potential, we fix some parameter, and we try to see if it is possible that the soliton can be trapped in the bottom of the effective potential well. The real parameter that we take is close to the vicinity of the parameter of the COD, the CO2 laser published by some researcher, and we see that by varying the frequency of our system, the effective potential should be so different behavior. It means that to have a stable solution, we can slightly varying the parameter such as the width of our cavity, and to find where we can have a good propagation. Thereafter, taking the parameter in the bottom of our effective potential of figure 5a, we obtained the result give in figure 6. That in the first line give the evolution of our electric field during the time. Figure A, it describes the evolution of solution with the solution C plus, and figure C describes the dynamic of the solution C minus. And then in the bottom, we have the corresponding frequency. We see that our system describes a stable periodic dynamic during the evolution time. Then, therefore, we can conclude that the localized solution can be trapped in the bottom of our effective potential. Also, we try to see how it is propagate does it propagate. It is why we plot the evolution of our vectorial electric field during the time as given in figure 7, and we see that in the first time, during the propagation of our solution, initially loose, we have initially we have the decreasing of the intensity and the shifting of our solutions thereafter become stable and propagate with the same position during the time. And in the bottom, we also have the spectra, and we see that our generated solution is first non-stable, thereafter self-confined, and becomes stable and show the stable dynamic with a conserved spectra. Also, we would like to see the impact of the kinetic couplet term on our dynamic. And the same as in the figure 6, we see that it is possible to have to the solution to be trapped in the bottom of the effective potential. And when taking the parameter in the bottom of the effective potential, we also observe another kind of dynamic. Here, we not have the periodic dynamic as presently observed, but here we have a quasi-periodic dynamic. It means that by varying the parameter of our laser and taking into account the effect of the higher nonlinearity, we can have different stable dynamic going to periodic to a stable dynamic and pseudo periodic dynamic. The similar dynamic have been observed in the electronic system. I'm describing some phenomena such as synchronization. And in order to see more on the evolution of our solution, we then plot and the t plus 1 dimensional form profile of our solution. The first panel have been obtained for the value of the cross coupling kinetic term as given and is 0 minus 0.25016, and we see that during dynamic the solution, the generated solution initially decrease. We initially have the decreasing of the intensity and the change of their shape, and progress to a top scripting shape solution that is self-confined and showing a stable evolution during long time of propagation. Thereafter, we increase the coefficient of the coupling cluster, and we also see that we have the fast shifting of our solution from the central position, and the top profile quickly scripting and showing a stable propagation, a very good stable propagation during the time. In order to confirm that the information is not lost, we also try to see their frequency, their spectral evolution, and we see that the spectral of our information remain conserved during the time of evolution. Therefore, we can conclude that in order to analyze the stability of the vectorial um, cavity soliton, laser cavity soliton, we used to take into account the higher order non-linearity, and to implement it, we can do it by monitoring, yes, the width of our cavity, also the intensity of the pumped electric field, and we can have a good stable uh, dynamic of our generated solution. In conclusion, in this presentation, we have summarized present the derivation of the tensorial nonlinear polarization of our Maxwell block model. And from the nonlinear perturbation analysis, we have also derived the vectorial cubic kinetic complex Gibbs-Lando modeling the interaction of an electromagnetic field with the matter in a laser near the lasing threshold. After, the stability of our system have been performed by analyzing the possibility of the soliton to be trapped in the bottom of the effective potential. Based on appropriate choice of the parameter belonging to the bottom of our effective potential, and through the numerical simulation based on the split-step Fourier methods, we show that we observe the good agreement between our analytical projection and the numerical evolution. In, at the end, we can say that the cross compensation involving data involve self-focusing, loss gain, and coupling effect can appear as a stabilization mechanism of the laser cavity solution This work can find application in the class B laser, and talking from class B laser, we have as example the COD laser model. Thank you, madam. Thank you for your kind attention. You have the floor, madam. Hello? Hello?
Thank you. Thank you, Dr. Alien, for your presentation. So, any questions from anyone? Okay, no questions, I think. Thank you once again for your presence and presentation. Yes. So our next presenter is Dr. Biswajit Panda from SN Bose National Center for Basic Sciences, India, and the title of the talk is Simultaneous Detection of Dual Species using Wavelength Modulation Spectroscopy for Atmospheric Monitoring and Breath Diagnostics Applications. Hello, Dr. Biswajit.
Hello, ma'am. Am I audible?
Yeah, hi. Yes, you are audible. So you are the presenter now. Please share your screen with us.
Yes.
Yes, we can able to see your screen. Perfect. Please continue.
Okay. Good morning, everyone. Myself, Biswajit Panda, a senior research fellow from SN Bose National Center for Basic Sciences, a institute in the Department of Science and Technology from India, working under the supervision of Professor Manik Pradhan. Today, I am going to present one of my recent work from our group on the topic simultaneous detection of dual species of two important trace gases, that is methane and nitrous oxide, using wavelength modulation spectroscopy technique for the application in atmospheric monitoring and breath diagnostics. The outline of my talk are as follows. In the background and objectives of my work, I will talk about the importance of nitrous oxide and methane monitoring in our atmosphere and also in human breath. And then I will give a brief introduction about the conventional absorption spectroscopy technique we normally use for the atmospheric monitoring, and I will talk about its drawbacks. Then I will brief about the basic principle of wavelength modulation spectroscopy technique that we have used in our experimental setup. Then in result and discussion, I will talk about the development of continuous wave external cavity quantum cascade laser based the WMS setup that we have developed in our lab. Then I will talk about the simultaneous measurement of N2 and CH4 spectra using the WMS setup. And finally, I will conclude my talk. So the main motivation of this work is mainly related to two important greenhouse gas in our atmosphere, that is methane and nitrous oxide. As we know, these two gases like methane and nitrous oxide are the second and third greenhouse gases in our atmosphere after CO2, and these two gases have both act as a biological messenger like N2O as a important gas in the denitrification and nitrification process in our body, also in our atmosphere. Also, methane act as a biomarker in the IBCS, like irritable bowel syndrome diseases. And these two gases have various anthropogenic activities, like have sources in human activities like industrial waste, agriculture waste, and fossil fuel burning. And if we talk more deeply, if we see the global N2O level uh, in from the last 10 years, it is increased by 3%, like from 322 parts per billion to 332 parts per billion. And in case of CH4, it increased from 1803 parts per billion to 1895 parts per billion, and increased by 5%. And these two gases have a greater stability in our atmosphere. So a slight change in the concentration in our human body or in our atmosphere always have an impact in a global warming and climate change also in our day-to-day life. So the main motivation to monitor these gases, and also the global warming potential of nitrous oxide that around 300 times greater than that of CO2, and also for methane it is around 25 times that of CO2. So the main objective of this work to develop a high sensitive optical sensor for that we can apply for the simultaneous detection of methane and N2O in both ambient air and also in human breath. So basically, for normal detection of trace gas molecules, we use. Hello, man.
Yeah, your screen is not visible to us.
Not visible.
No.
Just 1 second. What happened? Now,
No, it's still not visible.
what happened? It is showing that I am sharing the screen.
Yeah, now it is visible.
Sorry for the problem.
Yeah,
Uh,
you can
it is
continue.
okay. Now it is visible,
Yes,
right?
perfect. Yeah, it
Okay.
is visible. Yes.
Okay. So no, normal detection technique in normally we use direct emission spectroscopy technique. Like it is related to the Beer-Lambert's law that states that when a light of initial intensity like I0 pass through a medium, the output intensity I related to the initial intensity by a formula like I equal to I0 exponential of minus alpha d, where alpha is related to the concentration, that is x, of the sample by the formula alpha is equal to sigma x, where sigma is the absorption cross section of the particular absorption lines and alpha is the absorption coefficient and x is the concentration of the sample. So if you know the I and I0, you can calculate the alpha, and from alpha you can calculate the x, that is the concentration of the unknown samples, provided we should know the absorption cross section, that is sigma, of the particular spectral line belongs to a molecular species. But it has few limitations, like due to the single pass nature, the sensitivity is very low, like it up to 10 to the minus 4 to 10 to the minus 5 centimeter inverse. We can not measure up to like not in up to parts per million order, and it is very sensitive towards intensity fluctuations. So a very low signal in a large noise background cannot be detected. And again, due to the overlapping spectra of different molecular species, the selectivity of this technique is very limited. So now we have three problems. So the solution is like, for the selectivity, we have to use a high resolution laser source so that we can easily monitor 2 or 3 closely spaced spectral line of different molecular species without any interference from other molecular species for our application purposes. And for the sensitivity, we have to enhance the sample path length, that can limit the sensitivity like into parts per billion to parts per trillion order. And to reduce the fluctuation, we have to reduce the excessive 1 by f noise, that is the small frequency noise. So for the first selectivity case, we are using a laser known as external cavity quantum cascade laser. This laser provides the access to the entire mid-infrared region, that is around 4 to 25 micron region, and it is giving us the access the fingerprint region, which have the strong absorption features of fundamental and combinational vibrational transition of different molecular species that present in our atmosphere, and it can be monitored in our room temperature operation. And the most important thing is the narrow line width, that is using this narrow line width like 0.0003 centimeter inverse, we're operating at 7.8 micron region. We can easily select two closely spaced spectral lines of N2 and CH4 without any interference free of different molecular species like CO2 or H2O. This is the simulated spectra using Hytron in our laser region. You can see using this quantum Gaussian laser, we can easily probe different molecular species like CH4, N2O, H2S, C2H2, or CS, and other gas molecules. And next, for the sensitivity case, we are using a multipass cell in our experiment that is a path length around 76 meter in our case. And to reduce the excessive small frequency noise, we are using the technique that is wavelength modulation spectroscopy technique, such that if we modulate the laser source, that is the quantum cascade laser, in kilohertz region, the 1 by f noise, that is the pink noise, are reducing significantly, become constant, that is known as white noise region. That is the detection limit is shifting towards the high frequency region. Now I will explain how this wavelength modulation spectroscopy work and how we have introduced this wavelength modulation spectroscopy as a setup for the monitoring of CH4 and N2O. So basically, we have selected a two interference-free spectral lines of CH4 and N2O. Then the laser light, the laser source is modulated with a high frequency sine wave using a lock-in amplifier, so that when we scan the absorption pH of the particular absorption line, the interaction among the absorption species and the modulated signal generate a harmonic signal at the output that is demodulated using a high frequency lock-in amplifier. So basically, this modulation spectroscopy known as derivative spectroscopy, as we are getting the harmonic spectra at the detector by demodulating the signal using lock-in amplifier, like first harmonic, that is the first derivative, second derivative, and so on. So the important note is this modulation spectroscopy does not provide us any absolute spectra, that in case of like cavity ring down spectroscopy or direct emission spectroscopy, and the amplitude of second harmonic, that is the second order derivative, can be used for the calculation of sample concentration due to the highest signal to noise ratio. This is the schematic diagram of the wavelength modulation spectroscopy setup that we have developed in our lab currently. We are using a quantum cascade laser operating at 7.8 micron region. The laser light passes through from the quantum cascade laser source to the echostopic modulator, which diffract the light into two beams. One part of the beam is focused to the wave meter for the simultaneous monitoring of wave number, and other part of the beam is injected inside the multipass cell. After achieving the maximum path length, the existing light from the multipass cell is focused to the MCD detector using a off-axis parabolic mirror. Again, we are using a helium neon laser in visible region, that is 633 nanometer, for the alignment purposes. And we are using a lock-in amplifier from here we are giving a high frequency sine wave to the quantum cascade laser, and the demodulated signal from the lock-in amplifier is connected to the our computer for the data acquisition system. And for the scanning of the adjacent features, we are using a PJT driver which is connected to the ECQCL. From here, giving a voltage using the function generator for the scanning of the adjacent feature across the adjacent lines. So before the experiment, we have done some simulation work using our current experimental conditions using the Hytron database. And that is where we use the pressure around 25 torr, optical path length 76 meter of multipass cell, temperature is room temperature, and we have used like normal atmospheric conditions of CO2 like 400 ppm, H2 up to 25,000 ppm in our laser region, and we have selected two interference-free highest adjacent cross-section lines of CH4 and N2O. You can see here the CH4 line belongs to the mu4 band around wave number center is 1 to 97.8192 centimeter inverse with the adjacent cross-section of 1.13 10 to the minus 20. The N2O belongs to mu1 band and wave number center is 1 to 9708314. Adjacent cross-section is 1.6 10 to the minus 19. So that you can see easily where difference of wave number is around 0.025 can be easily proved without any interference of other molecular species that can be applied for the real-time application using our setup. So after the simulation work, we have optimized the twice f modulation signal that we are getting from the lock-in amplifier using two important parameters here, that is the modulation amplitude. We are giving the voltage from the lock-in amplifier and we have plotted the modulation amplitude versus the twice f amplitude that the output signal we are getting from lock-in amplifier for two molecular species, that is CH4 and N2O, and we have observed that with increasing in the modulation amplitude, the output signal is increasing significantly and becomes saturated after a saturation value, and then start decreasing due to the over pressure broadening of the gas molecules. And we have observed the same phenomena in case of pressure parameter, and we have found the optimum modulation amplitude in case of N2 and CH4 is around 2.8 volt, and that of pressure is around 25 torr. And this optimized parameter, that is the pressure and modulation amplitude, can be used to get the best highest signal to noise ratio for the real-time application. After that, we have given a relative spectra, that is a first derivative, second derivative, and third derivative spectra of CH4 and N2 here given here in the optimized condition. This spectra can be used, any spectra can be used for the real-time monitoring of N2. Then we have calibrated our optimized signal, or the twice of signal, because as we know, the output signal cannot only related to the concentration of the sample, also to the optical power and intensity fluctuations. So it is very much important to calibrate our experimental system to with the known concentration of the real samples like CH4 and N2O. Here we have taken different ppm different concentration of CH4 and N2O with known concentration. We have taken the twice spectra, and we have plotted the voltage versus the concentration here, a very and plotted fitted with the linear mathematical function. A very good collinear observation is observed between the twice m amplitude and different constant of CH4 here, and this calibration graph can be used for the calculation of unknown concentration of uh, twice voltage for CH4 and N2O. After this, we have applied our optical setup for the real-time monitoring of CH4 and N2O. We have taken the atmospheric sample from our from our center, that SNBOS center, and from breath sample from our one of the lab colleague, and we have taken the twice F spectra for both atmospheric sample and brain sample given here, and we have calculated the concentration of CH4 in atmospheric sample is around 1.95 ppm, that is parts per million, and the breath sample is around 2.25 ppm. In case of N2O, the atmospheric sample is found to be 490 parts per billion ppb, and breath sample is found to be 290 ppb, and we achieved a detection limit for both CH4 and N2O here is around 6 ppb and 30 ppb respectively. So in conclusion, I can say we have developed, designed, tested ultra high sensitive gas sensor using the WMS setup that is coupled with a quantum cascade laser, and the combined monitoring, real time monitoring of N2 and CH4 has been performed in both atmosphere, also in human breath, and this gas sensor has the potential to be study other trace gases in our laser region in future. I am highly grateful to my professor, supervisor Professor Manik Pradhan, for his guidance and support, to all my lab members and SNBOS National Center of Basic Sciences for the funding, and lastly to the conference organizer for organizing a nice conference and giving a chance to present my work. Thank you. Hello.
Yeah,
Hello, ma'am.
yeah, thank you, Dr. Biswajit, for your presentation. So, any questions? Okay, no questions, I think. Thank you once again for your
And
presence and presentation.
thank you, ma'am.
Yes. So our next presenter is Dr. Mohsen Chobani from University of Monastir, Tunisia, and the title of the talk is Optimization of the Second Harmonic Generation in INGAS Lens-Shaped Quantum Dots for Terahertz Applications, Impact of Pressure, Temperature, Electric Field, Indium Segregation, and in INGA interdiffusion. Hello, Dr. Mohsen.
Hello.
Yeah, hi. So you are the presenter now. Please share your screen with us. Yes, we can able to see your screen. Please make it a full screen. Yeah, perfect. Please continue.
If the screen is visible, I can start.
Yes, yes, it is visible. Please start your presentation.
Good morning to everyone. Thank you for this given opportunity to participate in this international conference. Thank you to Director M and Director Elisa. I hope you are doing well. I am Shubani Mahsen from the University of Monastir at Tunisia. Today I have the pleasure of presenting my research work based on optimization of the second harmonic generation in ENS GS lens-shaped quantum dots for terahertz application under combined effects of pressure, temperature, electric field, andium segregation, and EN andium gallium interdiffusion. This work was carried out in microoptoelectronic and nanostructure laboratory at the scientific faculty of Monastir at Tunisia. Well, the outline of my presentation will be as follows. After an introduction, I will present a brief history about the Carrier confined phenomenon. The third point will be dedicated to the linear and nonlinear optical properties. The fourth point will be devoted to the obtained results and discussion. And I will end with a general conclusion and some outlook. After the study of the massive semiconductor, the quantum well, and the quantum wire, the attention of researcher has turned to the quantum dots or zero-dimensional material, where the charge carriers are confined in three directions of space. In other words, there is 0 degree of freedom, and the density of states is discrete. This confined phenomenon gives energy levels confined in the conduction band and valence band. Therefore, transition between the energy levels of the conduction band are known by the inter-subband transition. However, we speak of the interband transition between energy levels of the valence and conduction bands. These transitions are exploited in electronic and optoelectronic fields, and several applications have been developed, such as laser diodes, photodetectors, and photovoltaic cell, and different semiconductor material are used. In this work, we searched to design a resonant structure with inter-subband transition in the conduction band in order to optimize the nonlinear optical properties using ENS GS quantum dots. A part of this work, or therefore, electrons and holes eigenstates and their envelope, their attributed envelope wave function are calculated via the resolution of the three-dimensional Schrödinger equation given in the envelope function and effective mass approximation. unlike other published works. In this work, we have introduced the position, pressure, temperature, and electric field effects. But the resolution of this equation is based on the implicit finite difference method of second order. More details will be to use this numerical method will be given later by Director Nabil. Therefore, under an intense incident electromagnetic wave of frequency omega, a nonlinear medium acquires a nonlinear electronic polarization. So the proportionality coefficient are called the linear susceptibility, the second harmonic generation, the third harmonic generation, and the nonlinear optical rectification. Under the density matrix formalism, the second harmonic generation coefficient is given by this equation. It is clearly seen that the second harmonic generation coefficient is inversely proportional to the incident photon energy and the transition energies between the excited and the ground states, and proportional to the geometrical factor, which is a function of the transition dipole matrix elements. To start, assuming lens-shaped quantum dot with radius r equals to 10 nanometer and height equals to 4 nanometer, the same structure was investigated by Maya et al. And the obtained photoluminescence spectrum shows two peaks with energy difference about 73 milli electron volt, which is attributed to the transition between the ground and the first excited states confined in the conduction band. Assuming homogeneous endium distribution at a fixed radius equals to 10 nanometer, the variation of the transition energies as a function of the quantum dot heights shows that our results doesn't match the experimental data. Therefore, we have modeled the endium distribution inside the wetting layer by Moraki's model, and inside the quantum dot by a Gaussian distribution. For these fitting parameters alpha, gamma, and beta, it is clearly seen that our results are in good agreement with experimental data for for the radius r equals to 10 nanometer and the quantum dot height equals to 4 nanometer. Therefore, atoms interdiffusion and endium interdiffusion inside the quantum dot and endium segregation inside the atoms intermixing inside the quantum dot and endium segregation inside the wetting layer phenomena must be considered in all remaining calculation and during the epitaxy process. To further understand the inhomogeneous endium distribution, the variation of the second harmonic generation coefficient as a function of the incident photon energy shows that when a non-homogeneous endium distribution is considered, The second harmonic generation spectrum shifts to higher energies, in other words, to the blue shift, and decreases in intensity. As well, the structure displays a resonant behavior at the resonant energy of the order of 73 millielectron volt, which is in good agreement with the experimental photoluminescence data. And the second harmonic generation spectrum presents two peaks. The minor peak was attributed to the absorption of one incident photon. However, the major peak was attributed to the absorption of two incident photon energy. So the considered structure can be used as a frequency doubler. To optimize we search to optimize the second harmonic generation coefficient, taking into account the bimodal quantum dots distribution as shown by the atomic force microscopy image. So we consider two ENS coupled quantum dots coupled to their wetting layer and embedded in GIS matrix. Therefore, the separation distance between quantum dots can be used as fitting parameters. For two strongly coupled quantum dots, when the separation distance is equal to 0 nanometer, it is clearly seen that the second harmonic generation coefficient is a non-monotonic function of the second quantum dot height. This phenomenon is due to the variation of the geometrical factor with the quantum dot height. As well, the second harmonic generation coefficient achieves its highest value for the second quantum dot height equals to 3.5 nanometer when both peaks were observed. For the now, donc, to more understand the interdot separation distance effect on the second harmonic generation, we plot the second harmonic generation intensities as a function of the interdot separation. It is clearly seen when the lateral coupling thickness is 0, the structure behaves like a molecule. However, when the lateral coupling thickness is more significant than 6 nanometer, the system under study displays a transition from two coupled quantum dots to uncoupled quantum dots, and the second harmonic generation coefficient decreases with increasing the coupled width between quantum dots. This phenomenon may be explained by the fact that the second harmonic coefficient is proportional to the geometrical factor, which will decline after 6 nanometer. So the structure, or in addition, it is clearly seen as by the figure, the right figure, that the structure has a resonant behavior in the terahertz domain. Therefore, the lateral spacer width between quantum dots will be set to 0 nanometer to achieve a more excellent second harmonic generation intensity, where the quantum dots are highly coupled. Uh, like other works, we have introduced the combined effects of pressure and temperature on the second harmonic generation spectrum. It is clearly seen that the transition energies display a blue shift with increasing pressure from 0 to 20 kilobar. This shift was attributed to an increase of the confinement potential and the electron effective mass with growing the hydrostatic pressure. And the opposite phenomenon is achieved when increasing temperature from 12 to ambient temperature. Therefore, pressure and temperature could be used as tuning parameters to adjust the nonlinear optical properties in the terahertz region. To make this study more consistent, we have introduced the electric field intensity and orientation in the second harmonic generation coefficient. The left figure shows that both peaks intensity of the second harmonic generation coefficient are proportional to the geometrical factor and decreases with increasing the electric field intensity. This phenomenon can be explained by the fact the applied electric field converts the confinement from the potential into a triangular shape and strengthen the asymmetry of the structure. Thus, a change in the matrix element and the geometrical factor were achieved. Consequently, the maximum intensity of the second harmonic generation was obtained for a negative electric field with higher intensity as illustrated by the right figure. And a blue shift of the spectrum was achieved with increasing the electric field intensity. Therefore, the electric field intensity and orientation could be used as tuning factors to adjust both the second harmonic generation peak position and magnitude in terahertz region. To summarize, in this work, we have tested and validated our implemented code based on the implicit finite difference method of second order. We have introduced the combined effects of interdot separation distance, pressure, temperature, electric field, and ion segregation inside the wetting layer and the atoms intermixing inside the quantum dot. It is found that endium segregation and atoms interdiffusion phenomena must be controlled during the epitaxy process and during calculation. As well, it is found that the second harmonic generation spectrum displays a red or a blue shift with adjusted intensity. In addition, the designed coupled lens-shaped quantum dots system can be used in terahertz region. Other nonlinearities will be also investigated and optimized under the mentioned external proofs. Now we are looking for collaborations with other laboratories in order to develop this work through an experimental study. There is several results are recently published in Physica B. Other results are submitted for publication in coming months. Finally, thank you for your attention and for this given opportunity to participate in this international conference.
Thank you, Dr. Mohsen, for your presentation. So, any questions from anyone? No questions, I think. Thank you once again for your presence and presentation.
Thank you, Director Anna.
Yeah, hi. So, as our next presenter, Dr. Usman is little bit busy now, so he will be joining in a few moments. So, in the meanwhile, Dr. Maria Lician has requested that she want to present now. So now we will have a talk on a novel lemma of the optical equivalence theorem, analytical formulation and applications. Hello, Dr. Orchidia.
Good morning. Can you hear me?
Yes. So you are the presenter now. Please click on, please share your screen with us.
Yes, I'll try to share the screen. Uh, how do I find the?
You need to click on the share icon you have on the screen, right? That is the
Yes,
third one.
I have the presentation open, but
Yeah. First,
no. Do I have to upload it on the internet?
no need. Upon clicking the share icon, what you can see on your screen.
I don't see the icon I want to share.
No. In the screen you have at the bottom, right? Four icons are there. You can see mic, camera, share, and leave.
Yes, and
You need to click on the share icon.
I am, but let's try.
Okay. Click on the share icon. Yes, now it is visible. Perfect.
No,
Yeah, we can able to see your screen. You can open your presentation.
let's see. I try. There is one screen more, so I try
Yeah,
again.
please close this one. Please close this one.
How do I close this window?
Yeah, you have the cross one, right? On the right side upper, on the top corner.
No, I only have a pin.
You have a cross close symbol on the top right corner. You can see left side top right corner.
I'll try again.
Uh,
I hope it should work now.
no, now it is not visible. Your screen is not visible to us.
I am trying.
Again, click on the share icon. Yes,
No.
now it is visible. Open the presentation. Open the presentation.
May I open the presentation by clicking
Yes.
on it?
Yeah,
Ca-
open that.
Can you click on that? Or should
No,
I
I
click?
cannot do that. You have to click that.
Can you
Yes,
see
now
the
it is on.
presentation now?
Yes. Yeah. Please continue.
So,
Yes.
thank you for your hospitality. I am presenting a new lemma of the optical equivalence theorem, and I will give analytical formulation and applications. And the last part is dedicated to envisaging an alternative research investigation guidelines with respect to the quantum Fisher information techniques. So the first part will be more mathematical. The second part will be more dedicated to physics applications. So the first part I go through step by step through the demonstration of, but quickly, through the demonstration of the optical equivalence theorem and of the lemma to be expressed. Then several applications will be given. Within the applications, there are optomechanical systems, quantum limits and quantum states, quantum mechanical noise in the interferometry, resonator techniques, Ramsey experiment, cold atomic ensembles, the relationship with the Heisenberg limit, and then with different types of metrology and Gaussian noises. So within the presentation of the lemma of the optical equivalence theorem, the approximations necessary for the applications of the new systems are calculated, and to do so, the new definitions for the operator, the states, and density matrix are explained. The purpose of the new lemma is to expand the density matrix at a new approximation order such that more information is appreciated from the data analysis. The optical equivalence theorem demonstrates the connections between the classical probability distribution formalism and the density matrix for a quantum mechanical system. There are several demonstrations for the optical equivalence theorems, and I am using one, for which the proof does not rely on the number operator, and this will also be useful for the formulation of the new lemma. If the number operator is not considered, it's possible to construct a diagonal density operator rho for coherent states, and it's possible to apply the other degrees of freedom, where for which the integration is extended on the Fock occupation space, where the annihilation operators and creation operators are defined. The interest in this demonstration is based on the fact that the hypothesis made for the states of the system, and in particular for unbounded observables, it's possible to replace the function defining the density matrix by another function whose support is controlled, and it is mostly useful for high momentum particles or almost infinite momentum particles. It is necessary to consider the weighting functions on a compact support, which can be further defined, which defines a new formulation of a density matrix. Then a change of variable is needed, for which the definition of a new weighting support control function is found, such that the density operator can be reduced to be finally diagonal. And the density operator is well defined, and it approximates a sequence of unbounded operators for the definition of a density operator, and which is still useful for the description of high momentum particles. it's possible to then expose quickly the new lemma for which a partition function can be expressed as a sequence of occupation numbers and can be explicitly calculated by means of a weighting support controlling function which obeys opportune properties with respect to the parameters which are used. And it is suited also for unbounded observables, which are observables of infinite momentum. This mathematical framework is particularly suited for extremely high energetic processes. The weighting support controlling function is based on a formalism which can be straightforwardly extended to the convergence properties in the trace class norm as well as through the definition for the orthonormal basis of the unbounded observables by transitivity, where it's possible to formulate suitable higher order corrections. And for the state for the operators which acts on the states and of which the expectation value is needed, it's possible to construct a weighted density matrix with specified spectral components on which are defined on compact support and in which a projector is therefore well defined. From this, the first approximation orders are depend on the definitions of the parameters which define the weighting support controlling function. The first approximation corrections have a specifying functional dependence on the definitions of the parameters which are used. The results obtained are those who descend from considering the properties of quantization of unknown hypersurface quantization techniques. The power spectrum of the operators is therefore defined and it can be decomposed as a sequence of elements which are obtained after the majorization of the operators after those of the weighting functions. The power spectrum is therefore not needed to be expressed as a sequence of majorizations where they do not apply to pure states. And in comparison with the quasi-probability distribution for density operators for an infinite momentum, which involves a Fock representation, the infinite momentum states can be studied. A suitable approximation for states in extremely high intensity laser fields, for example, whose energy can be compared as a limit going to infinity. There are some quick remarks. One remark is about pure states in the momentum representation, and where a weighting function allows one to classify coherent states and incoherent states in a radiation background field according to the properties of the radiation background fields. And more in particular, coherent states are represented by a finite number of creation operations which have as coefficients arbitrary complex numbers. And weighting functions can be defined which are tempered distributions and from which states are found as a finite number of creation operators in the Fock representation. And Weighting function is a linear combination of two-dimensional functions of a finite number of its derivative, and the two-dimensional functions can be defined after the same parameters which have been used for the weighting support controlling functions. The density operators in the momentum representation are weighted functionals, and the quasi-probability distributions are expectation values for the chosen density operators, and there are integral representations for the density operators, whose definition can be adapted also for incoherent states. For which temperate distributions are obtained, can be obtained only for pure states, as far as the density operators are concerned. The puzzle is solved by a representation of the density operator in the case of almost infinite background field independent of the POC representations. And the differences between the states are expressed in the power spectrum for optical systems as depending on the two parameters chosen for the extension of the theorem, and a corresponding Fourier decomposition can be found. We can now go to the applications whose presentation will have the purpose of the characterization of the physical properties. So the math part is now completed. It is possible to consider optomechanical systems for which there have been studies, both numerical ones and analytical ones. They concern the Wigner quasi-distribution. And in particular, the long time limit for their estimation can be calculated as with the power spectrum, which depend on a real parameter, mechanical resonance frequency, and the damping rate. The new lemma is now applied, and a new correction term is found. The correction terms consist of is due to the presence of the parameters of the weighting support controlling function, and allows one to improve the estimation of the power spectrum. Oh, sorry. I do apologize. Here I am. For this, the Fourier decomposition is possible of the modes corresponding to a system of an intense laser beam, and it's possible to define its characterization also on a Minkowski spacetime, and it can be applied also to analyze the properties of semi-classical optical systems. And also for intense laser beam modes as a complete formulation of the optical equivalence theorem. Our next application is to consider quantum limits of the states, for which the standard quantum limit in estimation has an estimation precision scaling with a determinate law, and to compare them with entangled particles which have a different scaling law, where the quantum frequency estimation for the qubits is characterized with Markovian noise. Interferometry experiments can also be considered, where photon counting error and radiation pressure error are error in the determination of distances with respect to the beam splitter, and then cannot be smaller than the standard quantum limit. As a contrast, a squeeze state technique can be applied with the definition of quasi-probability densities. A further application is one dealing with optomechanically induced lights, where the procedure is one to study the properties of the steady states, and the experimental apparatus should be endowed with ideal optomechanical induced transparency and inverted transparency window, where the decay rate of the active cavity and that of the passive cavity are considered. The presence of a probe field allows one to further characterize the system, and the response of the probe field can be investigated as far as the coupling with of the cavities and the resonator at some opportune frequencies which are now discussed. In particular, one can define ultra-slow light and ultra-fast light. In the case of ultra-slow light, it's possible to calculate the maximum time delay at the transparency window, and if the decay rate, the gamma m, if gamma m, if the decay rates of the difference in the decay rates is small, the maximum time delay can be calculated again. In the case of ultra-fast light, there are, for the same quantities, different, that is, for the evaluation of the different values acquired by the maximum time delay at the transparency window are found. Then the new lemma of the optical equivalence theorem is applied, and for ultra-slow light, a new result is found, for which when the difference in the decay rates is very small, the two minimum time delay at the transparency window are found to exactly match. In the case of ultra-fast light, the maximum time delay calculated in the two instances does not produce matching results. So far, a new difference has been found. The case of the optical resonator can be studied as well, and in particular for Fabry reference interferometers, the frequency variation associated with the opportune noise limit can be studied, and the measures on the average time as well. Frequency fluctuations are appreciated, and high sensitivity of detection of resonance is can be calculated, and in particular the average time is calculated such that the states are discriminated after the photodetector quantum efficiency. Further application which I only mentioned before going to the final applications is that the new lemma can apply to experimental apparati such cold atomic ensembles, cold atomic trapped ions, temperature jump experiments for protein folding, jump processes between states, quantum correlations of multispatial modes for Gauss-Markov models, and uncertainty estimations of many approaches to metrology. Then it's possible to go through spectroscopy experiences, and in particular to analyze the Ramsey experiment, for which the signal sensitivity is defined, but is found to saturate very early. Nevertheless, it's possible to define the signal sensibility after application of the new lemma, where new orders, depending on gamma and tau, and on n, a new dependence on n is found. The saturation, the description of the saturation after the application of the new lemma is also improved, and it contains only a determined power of the time. Cold atomic ensembles can be considered, in which a signal to noise ratio is defined, and it depends on the excited state decay rate and on the probe detuning. The new after the application of the new lemma of the optical equivalence theorem, a signal to noise ratio is calculated, and the new role of the decay rate as power 2 is found, and the approximation order of the next order of decay rate is demonstrated to be power 4. The same methods can be applied to high signal to noise ratio laser technique for accurate measurements of spectral line parameters. The study of the Heisenberg limits allow one to study the probes of non-interacting particles and their scaling, and the effect of the shot noise in the quantum limit as far as the uncertainty is concerned. It is therefore possible to study what happens if one wants to analyze, to apply the new lemma to the quantum limit of noisy metrology. And for this, non-Hermitian quantum sensing has to be studied and investigated, and it's possible to study the uncertainty of an unknown frequency to be estimated, for which fundamental limits of non-reciprocal approaches in non-Hermitian quantum sensing are found, and the classical system, the uncertainty for the classical system of n independent qubits is known as far as in the quantum approach for the optimal time parallel noise application of the new lemma of the optical equivalence theorem leads one to the new definition of delta omega the uncertainty, where the powers are the powers of time are decomposed, and the remainder, the exact order of the remainder is calculated. The study of Gaussian white noise and coupling with quantum system is based on functional methods, which are integration over the noisy field in the evolution operator and the equivalent non-Hermitian Hamiltonian, and whose features are described by dissipative dynamics obtained after integration over the noisy field. And there is again contribution from the fluctuations and in a different manner it's possible to appreciate the variation of space localization and time localization if new non-Hermitian interactions are considered. As an application to quantum system, to non-Hermitian systems, it's possible to have to study the nonlinear perturbative regime. And in the nonlinear perturbative regime, the complete Hamiltonian is is a non-Hermitian one, and where the features of the system are modulated after a small parameter, a parameter epsilon small at leisure. And the Hamiltonian defined after the parameter epsilon can be characterized is after the application of the new lemma of the optical equivalence theorem with the estimation improved after integrating the output field over a long time duration of the tau, and more in detail, the non-diagonal elements can be expanded and calculated to be higher order by means of the weighting function, which is obtained after the new lemma of the optical equivalence theorem. The same methods can be applied to quantum metrology, noisy channels, precision limit in noisy quantum and enhancer metrology, quantum metrology with quantum error correction, noise robust quantum sensing, determination of the asymptotic limits of adaptive photon counting measurements for coherent states, and other branches of non-Hermitian physics. So I would like to thank you for your attention, and I'm ready for questions. I think I'm on time. Can you hear me?
Thank you, Dr. Orchidia, for your presentation. So any questions from anyone? Okay, no questions then. Thank you once again for your presence and presentation.
Thank you for the great opportunity I have been given. I'm grateful for your hospitality to the conference.
Thank you. So, so our next presenter is Dr. Osman Adguzel from Firat University, Turkey, and the title of the talk is Crystallographic Aspects of Shape Reversibility in Shape Memory Alloys. Hello, Dr. Osman.
Thank you very much.
Yes, so please you can share your screen with us.
Hello.
Yeah, hello.
Unfortunately, the sharing button is closed in my computer, and I cannot share PPT of my talk. Screen is open, but I couldn't see any document to share to presenter.
What is showing? What is the error you are getting over there on clicking the share icon?
If you can provide an email, I can send you the PPT of my talk.
Okay, so you want to share from our side? You can reply to the conference organizer. You can send your presentation to her and we will
Yeah,
share from
okay.
our side. You can send to Ashley and we will play from there.
I sent PPT of my talk to Ashley,
Okay, okay.
and
Just give me a moment. We will just check it, the email.
yeah, okay. Did you receive it?
Yeah, just a minute. Let us
Yeah,
check.
okay. Thank you very much. Yenisi başladı. 3 taneydi bu. Can I start my presentation? Hello? Can I start my presentation, please?
Yeah,
Can I
hi,
start
Dr.
my...
Osman. Yeah, please start with the
Yeah,
presentation.
okay, thank you very much. Good morning, good afternoon, and good evening, distinguished scholars, colleagues, participants, speakers, and moderators at the different locations on the globe of the world. First of all, I wish like to introduce my sincere thanks to the conference committee, conference management, and conference company to provide me a facility to deliver my talk at this important conference. Let me inform you that this is a multidisciplinary conference, and I am sure you agree with me that every scientist is not familiar with every subject of the science. Therefore, at the beginning of my talk, I will introduce the basic terms and definition related to the crystallography of shape memory effect and superelasticity in shape memory alloys. Next slide, please. Next slide, please. Thank you very much. Shape memory alloys are thermoresponsive materials and exhibit a peculiar property called shape memory effect. This phenomenon is initiated with the thermomechanical treatments on cooling and deformation and performed thermally on heating and cooling, with which shape of the material cycle between original and deformed shape in reversible way, and this behavior can be called thermal memory or thermoelasticity. This is plastic deformation due to the soft character of the material in low temperature condition, and deformation energy is stored in the material and released on heating by recovering the original shape. These alloys exhibit another property called superelasticity, which is performed with mechanical stressing and releasing at a constant temperature in the parent phase region of the material. Therefore, this behavior can be called mechanical memory. Next slide, please. This is the main processes for shape memory effect and superelasticity. For the shape memory effect, materials are deformed in the low temperature condition, and upon releasing, material keeps the deformed shape due to the plastic deformation. After that, on heating, material record the original shape and shape of the material cycle between deformed and original shapes on cooling and heating in reversible way. For the superelasticity, materials are stressed in elasticity limit in the parent phase region and upon releasing record the original shape by exhibiting elastic material behavior. Next slide, please. Shape memory effect is result of the crystallographic reactions, thermal and stress-induced multicyclic transformations, and evaluated by the structural change in atomic scale and crystallographic level. Shape memory effect is performed thermally in a temperature interval depending on the forward Austenite martensite and reverse martensite Austenite transformation on cooling and heating following the first cooling and deformation processes. Superelasticity is also a result of the stress-induced multi-state transformation and performed with mechanically stressing and releasing inelasticity limit at a constant temperature in the current wave region. Next slide, please. This is the temperature hysteresis of shape memory alders on cooling and heating. Thermal induced multi-state transformation occurs on cooling and start at MS temperature and completed at MF temperatures. After that, on heating, reverse austenitic transformation start at AS temperature and completed at AF temperatures. MS is Martens's start and MF is Martens's finish temperature. Also, AS is austenite start and AF is austenite finish temperatures. Next slide, please. These are the stress-strain characteristics of shape memory effect and superelasticity. As I stated, for the shape memory effect, materials are deformed in the low temperature condition. As you can see, stress-induced multi-state transformations occur at the plateau level with the deformation and stressing. As you can see, early stage of deformation exhibits elastic material behavior. Also, as you can see, stressing and relation paths are different for superelasticity, and hysteresis lobes refers to the energy dissipation. Next slide, please. Shape memory behavior evaluated by the microstructural change in atomic scale caused by the internal stresses and shape change occurs in the bulk level. Shape memory effect is governed by thermal and stress-induced multi-state transformations. Thermal-induced multi-state transformations occur with the cooperative movements of atoms by means of lattice invariances in one monotype direction on the one monotype planes of austenitic matrix, and other parent phase structures turn into the twinned multi-state structures. After that, twinned multi-state structures turn into the detwinned multi-state structures by means of stress-induced multi-state transformation with the deformation in the low temperature condition. Superelasticity is also governed by stress-induced multi-state transformation, and ordered parent phase structures turn into the detwinned multi-state structures with the stressing in the parent phase region. Next slide, please. This is the schematic of shape memory cycle in the crystallographic level. Let me inform you that shape memory effect and superelasticity is observed in the beta phase region of the material, and ordered phase structure is essential for the quality of shape memory effect and superelasticity. As I stated, for the shape memory effect on cooling and deformation, first step is cooling, and on cooling, ordered parent phase structures turn into the twinned multi-state structures by means of thermal induced multi-state transformation. With the deformation, twin structures turn into the detwinned multi-state structures by means of stress-induced multi-state transformation. Following this treatment, detwinned multi-state structures turn into the ordered parent phase structures on heating by means of reverse austenitic transformation. After that, crystal structure of material cycle between detwinned multi-state structures and ordered parent phase structures on cooling and heating in reversible way. It is important that detwinned multi-state structures occurs with mechanical stressing in the first step, but in this cycle, detwinned multi-state structures occurs on cooling. Next slide, please. This is also schematic of superelasticity. For the superelasticity, materials are stressed in elasticity limit in the parent phase region, and ordered parent phase structures turn into the detwinned multi-state structures by means of stress-induced multi-select transformation. After that, upon releasing, the twin structure turns into the ordered parent phase structure by means of reverse austenetic transformation. It is important that this cycle is completely mechanically for superelasticity, but the same cycle is thermally for shape memory effect. Next slide, please. Superelasticity is also linked with the stress-induced multi-select transformation, which is induced by applying only mechanical stress in the parent phase region, and with the stress, parent austenate phase structure turn into the completely determined multi-select structures, as in the deformation setup of the shape memory effect, and twin multi-select structure turn into the parent phase structure upon releasing. Also, crystal structure of material cycle between determined multi-select structures and parent phase structures on stressing and releasing. Stress and strain curve exhibit nonlinear behavior for superelasticity. Stressing and releasing paths are different, and hysteresis lobes refers to the energy dissipation. Next slide, please. This is the stress strain characteristic for superelasticity. As you can see, stressing and releasing paths are different, and hysteresis lobes refers to the energy dissipation. Next slide, please. Martin-Selick transformation is a first-order solid-state phase transition and occurs in a fifth step with the cooperative movement of atoms in displacing manner. Therefore, these transitions have diffusionless character, and product Martin-Selick phase inherits the order of parent austenetic phase. Martin-Selick transformations may occur in two basic steps in the beta phase region of the material. These are Bain distortion and lattice invariant shares. Next slide, please. These are the basic beta phase structures in the beta phase region of the material. First figure represents the ordinary body-centered cubic structure. Second figure represents the cesium chloride type superlattice structures. Third figure represents the DO3 type superlattice structures mainly observed in ternary couple shape primary alders. Also, last figure represents the L21 type crystal structures in the beta phase region of the materials. Next slide, please. Bain distortion is mainly effective in ternary couple shape primary alders and consists of an expansion of 26% in 001 type axis called Bain axis and a compression of 11% in the 110 type direction perpendicular to the Bain axis. There are three Bain axes. These are cube axis, and these are 100, 010, and 001, and BCC-based unit cells turn into the body-centered tetragonal structures as three variants with different orientations. Next slide, please. Lattice invariant shares occur in as Martenset variant on one monotype planes of the austenite matrix, which is basal plane of the martensite. And these shares occurs in two opposite direction, one monotype direction on the one monotype planes. One monoplanes family represents 6 certain planes and totally 24 Martenset variants with lattice invariances. These planes are as follows: 110 minus 110, 101 minus 101, 011, and 01 minus 1. Next slide, please. The lattice invariance and lattice twinning is not uniform in coupled shape memory alders, and their shares cause to the formation of layer structures. 1-type planes of the parent phase, these are main places, turn into the unusual layer structures which consist of an array of closed packet planes with complicated stacking sequences called as 3R, 9R, or 18R martensite, depending on the stacking sequences on the closed packet planes of the ordered lattice. The periodicity and therefore the unit cell is completed through 18 layer in directions that in case of 18R martensite structures in ternary coupled beş yapmamaları ağırlar. Next slide please. This is the formation of layer structure with lattice invariances. First figure represents the stacking of 1-type planes of austenite matrix with the lattice invariances. The stacking turn into the layer structure with stacking sequences ABC, BCA, CAB, and A and others for 18R martensite structures in ternary coupled beş yapmamaları ağırlar. Next slide please. These are the basic terms and definitions related to the shape memory effect and superelasticity. As you can see, experimental studies were performed on two copper-based shape memory alloys. These are copper zinc aluminum and copper aluminum mangan alloys. You can see alloy composition and this composition were selected in the beta phase range of the material. As you can see, martensite start and martensite finish temperatures are over the room temperature for both of the alloy samples, and these alloys are in the martensitic state at the room temperature. Next slide, please. Specimens obtained from these alloys were solution treated for homogenization in the beta phase field as following, then quenched in ice, brine, and aged at room temperatures. These temperatures are 830 and 700 degrees for copper zinc aluminum and copper aluminum mangan alloy samples, as these temperatures were selected in the beta phase region of the materials. Powder specimens for X-ray examination were prepared by filling the alloys, and the specimens were sealed in evacuated quartz tube and given the beta phase homogenization treatments in order to release the strain effects. These temperatures are 830 and 700 degrees for copper zinc aluminum and copper aluminum mangan alloy samples, and these temperatures were selected in the beta phase region of the materials. Powder diffractorants were obtained for all the specimens at the different stage of aging in a long time interval. Next slide, please. This is an X-ray diffractoram taken from copper zinc aluminum alloy samples after long-term aging at room temperature for about 15 years after quenching. As you can see, peak intensities and peak characteristics are different, and this diffractoram exhibits superlattice reflection. It is important that these plane pairs are important for ternary coupled beş yapmamaları alloys. These are 122, 202, 128, 208, 110, 210, and others. Next slide, please. This is another X-ray diffractoram taken from copper aluminum mangan alloy samples after long-term aging at room temperature for about 15 years after quenching. As you can see, this diffractoram also exhibits the same characteristic with these plane pairs. Next slide, please. A series of X-ray diffractorams have been taken from both of the alloy samples in a long time interval, and some change have been observed in the diffraction angles, peak intensities and peak characteristics with age and duration. In particular, some of the successive peak space shift toward each other, and these peaks provide the following relation between Miller indices for 18R multicyclic structures in ternary coupled yapmaları alloys. This plane pair can be listed as follows, as I stated on the different theorems. For 18R multicyclic structures, 1 to 2, 202, 1 to 8, 208, 1 to 10, 210, 040, 320, and others. At the long-term investigation, it is observed that this peaks pairs come close each other with age and duration, and this change reveals the changes in the crystal structure of the material. Next slide, please. Also, this change refers to the rearrangement of atoms in this disordered manner in the martensite state. The basal plane of the martensite, 1-1 type plane, is subjected to the hexagonal distortion with martensite formation, on which atom size have important effect. In case the atoms occupying the lattice size have the same sizes, the basal plane of martensite becomes regular hexagon. Otherwise, the deviations occurs from the hexagonal arrangement of the atom in case atom size are different. In the disordered case, all of the lattice size are occupied randomly, and atomic sizes can be taken approximately equal each other. In the ordered case, lattice sizes are occupied regularly by certain atoms which have different atomic sizes, and basal plane deviates from the regular hexagonal arrangement of atoms due to the atom size differences. Next slide, please. This is the basal plane of the martensite, and rectangular shape of the basal plane turn into the hexagonal shape by means of martensite transformation. In the disordered case, we don't know which atom occupies which lattice size, and we can take atomic sizes approximately equal each other, and hexagon becomes regular hexagon. In the ordered case, atomic distribution is regularly, and neighbor atom size are different, and deviations occur from the hexagonal arrangements of atoms due to the atom size differences. Next slide, please. Second experimental study were performed on electron microscope by taking electron diffraction patterns and image of surface and interface of the material. These are the electron diffraction patterns taken from both of the alloy samples, and as you can see, electron diffraction patterns also exhibit superlattice reflections. Next slide, please. Conclusion. Shape-memory effect is evaluated by the structural change in microscopic scale by means of multicyclic transformation. The fundamental structure of the beta-type martensites are orthorhombic closed packet structures, which consist of an array of closed packet planes in couple-based yapmaları alloys. The beta-type martensites have the layered structures, and they are characterized by the stacking sequences depending on the order in the parent wave region. These couple-based ternary alloys have the DO3 type superlattice structure in the parent wave region, and the following stacking sequences occur with the martensitic transformation. And the sequences are AB, CB, CA, CA, BA, BC, BC, AC, and AB for 18R martensitic structures in ternary couple-based yapmaları alloys. Based on the austenite-martensite relation, the basal pinene of 9R or 18R martensite originates from the 1 monotype planes of the parenthase on which lattice invariances occurs in the 1 monotype direction during the martensitic transformation. Next slide, please. These are the references. And next slide, please. Thank you very much for your attention. If anybody has question, I will try to answer. I think there is no question, no comments. These are the basic scientific statement. If I can read it the way we see it, physics has too many gray area already. Thanks again to listen my talk, and I wish you great success at the next part of the conference.
Thank you, Dr. Osman, for your presentation. So, any questions from anyone?
Thanks again to listen my talk.
Okay, no questions. Then thank you once again for your presence.
Thank you very much to you too.
Thank you. So our next presenter is Dr. Nabil Benzirog from University of Monastir, Tunisia, and the title of the talk is Electric Field Pressure and Temperature Effects on the Optical Absorption Coefficient in INGAS strained quantum dots under indium segregation and INGA intermixing phenomena. Hello, Dr. Nabil.
Hello, do you hear me?
Yeah, hello. Yes, can you please speak louder?
Hello, do you hear me like that?
Yes, yeah, now it's perfect. Yes. Please share your
O-
screen with us.
Okay. Yes. Is it shared?
No, it's not visible now.
Is it shared now?
No.
Okay, I'm waiting for it.
Yes, your screen is visible. Yes. Yeah, hello, Dr. Nabil. Hello. Hello.
Hello? It is activated the
Yeah.
micro?
Yes, we can able to see your screen. You can start your presentation.
Okay, thank you very much. So, good afternoon, everyone. Firstly, we thank the Scisynopsis organization for this international conference. In this oral presentation, we will begin to explore the electric field, pressure, and temperature effects on the optical absorption coefficient in indium gallium arsenide under gallium arsenide, strained quantum dots under indium segregation, and indium gallium intermixing phenomenon. This study will begin by an introduction, followed by the general properties of semiconductors materials indium arsenide and gallium arsenide. After that, the numerical method used and nonlinear optical properties. Thereafter, the results and discussions, and finally the conclusion and outlook. Originally, the effect of quantum confinement is manifested by the discretization of permitted energy levels in one or more directions of confinement, as well as the change in the density of states as a function of the carrier's energy. The various possibilities of confinement in a semiconductor are realized according to the limitation of the movement of the load carriers in zero, one, two, or three directions of for massive materials, we are talking about 3D materials, that is to say, a crystal where all the carriers move freely in the three directions of space, while in a quantum well named by the 2D materials, the carriers possesses 2 degrees of freedom and are confined in one direction. In in the case of the quantum wire, we are talking about one-dimension material. That is to say that the confinement is in both directions x and y with a single degree of freedom z. In the case of quantum boxes or quantum dot, carriers are confined in all three directions of space and are considered structure 0D as carriers have 0 degrees of freedom. The density of states of this nanostructure is discrete, and electron transitions between different energy levels produce photons. While this characterization is due to the atoms from which they named them artificial atoms. More precisely, the phenomenon of confinement quantum confinement allows the bound structure of these various quantum dots to have two types of transition: that which is between the two energy levels of the conduction band and the valence band is called interband transition, and that between the confined energy levels of the same band is called intra-band transitions. However, the exploitation of the electronic, optical, and optoelectronic properties has made us understand that these quantum dots have a diverse possibility of the applications in many devices covering ultraviolet laser diode, photodetectors, and photovoltaic cells, etc. For this, we studied the nonlinear optical properties of indium gallium arsenide and gallium arsenide, where we must understand at first the general properties of indium arsenide and gallium arsenide. The structure properties of the gallium arsenide and indium arsenide materials have shown that their crystalline structure is zinc blende, as we can see in the left figure. The right figure shows the band structure of both materials. The both massive materials semiconductor have a direct energy band gap in the gamma point. We grouped on the table below the values of the lattice parameters and the spin-orbit coupling energies for the two materials, since the width of the forbidden band and the factors on which it depends are essential to know in the optical properties. In this work we have introduced the dependence of the energy gap with temperature given by Varshni's law, and also the dependence of the energy gap with pressure. These figures shows that the energy gap decreases with increasing temperature and in the gallium arsenide, which plays the role of barrier material. However, the energy gap increases with increase of pressure. For the both materials, the parameters used are summarized in the table upper. The change in the gap energy also affects the effective mass. We have introduced also the pressure and temperature effects on the electron effective mass via the energy gap as given by Vergaft-Mann-Eyal formula. As it is shown, the electron effective mass decreases with increasing the temperature, and the opposite phenomenon is observed with increasing the pressure. Consequently, temperature and pressure effects will affect the confinement energies E and then the nonlinear optical properties. In this present study, we solved the stationary 3D Schrödinger equation where H is the Hamiltonian of the electron, E and psi are the eigenenergies and their attributed wave functions at x, y, z positions, which is equal to the equation below. The problem here is how to solve this equation. However, the Schrödinger equation cannot be solved analytically due to the geometrical complexity of the structure under investigation. So, to calculate the carrier's confinement energies and their associated wave functions in indium-gallium arsenide, there are in the literature several numerical methods allows the resolution of the Schrödinger equation, like spectral method, finite element method, finite volume method, finite difference time domain method. The finite difference method is the one used in this work. In order to apply the finite difference method, the space domain Lx, Ly, and Z thickness must be divided into n-1 power 3 intervals, each of which is of length delta. The spatial domain is thus cut into a mesh where each point I is marked on the x, y, and z axis by its position r, as shown in the figure, which are called the nodes of the mesh. Thus, the spatial domain is discretized in n, x, and y, and z nodes. The problem now is to determine n, x, and y, and z nodes discrete values of unknown size of function at the different nodes. The basic idea of the finite difference method is based on the development in Taylor series of functions around the point R, which brings us back to nx, ny, and z linear equations. By using the central finite difference approximation for each of the second-order derivative, we will get the two-order diagram, said centered to approximate the derivative first and second function, indicating that the truncation error tends towards zero as the power of 2 delta Z under 2, and that's why it's called method order. However, with using the standard boundary conditions, the problem now is to solve n-2 power 3 linear equations represented by this matrix. After the diagonalization of the Hamiltonian, we could calculate the direct numerical solutions for the electron energies, states, and their matching wave functions. Thus, it gave us the possibility to explore the nonlinear optical properties. In optics, the origin of nonlinear effects lies in the strong interaction between a light wave and the material it passes through. Then the medium becomes polarized. Under an intense incident electromagnetic wave of frequency omega, the nonlinear medium acquires a nonlinear electronic polarization where the coefficients are known as the linear susceptibility, second harmonic generation, third harmonic generation, and nonlinear optical rectification. Under the density matrix formalism, the total absorption coefficient is the sum of two contributions, the linear and nonlinear absorption coefficients, which are function of the incident photon energy, the transition energy, and the dipole matrix element. To start, we considered the lens-shaped indium-gallium arsenide quantum dot having a radius r and a height h, coupled to its Witten layer. In this work we have introduced the indium segregation inside the Witten layer using Moraka's model and the indium-gallium intermixing effects inside the quantum dot modeled by a Gaussian distribution. The next figure shows a two-dimensional indium distribution. To validate our implemented code, we considered the same structure investigated by Maya and coworkers, where the low-temperature photoluminescence spectrum shows clearly minor and major peaks. The strongest peaks the strongest peak, located on the first experimental energy, is attributed to the optical transition between the ground states E1 confined in the conduction band and the ground states HH1 in the valence band. However, the lowest peak close to the second experimental energy is related to recombination from HH1 in the valence band to the first excited state in conduction band. Accordingly, the inter-subband transition energy the inter-subband transition energy between the ground and first excited states is 72.8 millielectron volts. In order to find out which indium profile adequately describes the actual emission spectrum, we calculated the interband transition energies as a function of the quantum dot height for a radius of 10 nanometer in the low temperature of 12 Kelvin. As shown, for a pure indium arsenide under gallium arsenide quantum dot, the obtained results were far from the estimated dimensions of 4 nanometer of height and radius of 10 nanometer, and did not validate the experimental transition energies even when the nominal indium composition was decreased from 1 to 0.6. However, assuming inhomogeneous indium distribution in the quantum dot and for the segregation phenomenon in the Witten layer, the obtained results were closer to the measured photoluminescence peaks for H of 4 nanometer and R 10 nanometer, as confirmed by the experimental data. Hence, the obtained results showed that the third-order nonlinear contribution is just a negative fraction of the linear one, and the linear one is a positive fraction of the total. Therefore, the total absorption coefficient is reduced, and this structure has a resonant behavior of the transition energy of 72.8 millielectron-volt, which is in excellent agreement with the experimental photoluminescence data. To further understand the indium segregation and indium-gallium intermixing effects, we performed our simulations with or without these phenomena. As compared to the reference sample, which is the spectrum A, the inclusion of the indium segregation in the within layer led to a blue shift of the absorption spectrum with the same intensity. This can be explained as follows: for pure indium arsenide quantum dot, the confinement potential along the growth axis can be considered as a square quantum well. However, the inclusion of the indium segregation changes the confinement potential into a triangle form, followed by an increase of the transition energy between the first excited states. However, according to spectrum C, the inclusion of the indium-gallium intermixing effects inside the quantum dot led to a decrease of the absorption magnitude or by a factor of 64%, followed by a red shift of the spectrum. Therefore, assuming a homogeneous indium distribution along the radial and vertical directions revealed that the indium composition tended to zero before reaching the maximum radius of 10 nanometer and height of 4 nanometer. This makes the quantum dot under investigation slightly lower than the initial lens-shaped quantum dot. Consequently, a 23 millielectron-volt red shift of the absorption spectrum was obtained. However, the absorption coefficient intensity decreased due to an increase in the nonlinear contribution, which is affected by a change of the dipole matrix element. Accordingly, to more understand the behavior of the absorption coefficients of this quantum dot under the combined effects of temperature and pressure, we plotted this figure. One may notice that the transition energy decreased with temperature increase. This red shift originates from decreasing the confinement potential and electron effective mass with increasing temperature from 12 to 300 Kelvin. However, the opposite phenomenon was observed upon the increasing the hydrostatic pressure from 0 to 20 kilobar. To explore the influence of the electric field intensity and orientation, we studied the linear, third-order nonlinear, and total absorption coefficients with three different electric field values. Accordingly, as the electric field is negative, the absorption coefficient's peak positions showed a redshift, which is attributed to the decrease of the energy difference between the first lowest energy levels. However, the opposite phenomenon is observed for an applied positive electric field. As a result, nonlinear optical properties underwent an apparent linear Stark effect under an applied electric field. Finally, our theoretical results showed an excellent agreement with the experimental photoluminescence data. Combined effects of indium segregation, atoms intermixing, pressure, temperature, electric field, and quantum dot dimensions implies significant effects on the linear and nonlinear optical properties. The external electric field can be used to strengthen the asymmetry of the confinement potential and the degree of overlapping between the confined states. The linear and nonlinear optical properties in strained lens-shaped quantum dots can be adjusted for optoelectronic devices. Finally, one can outlook for the investigation and optimization for other nonlinearities and their combined effects of the external proofs mentioned above, such as the refractive index change, nonlinear optical rectification, second harmonic generation, and third harmonic generation. Thank you for your attention. Mrs. Emma, I
Thank you.
finished.
Yeah. Yes. Thank you, Dr. Nabil, for your presentation. So, any
Thank you.
questions from anyone? Okay, no questions then. Thank you once again for your presence and
Thank,
presentation.
thank you, Mrs. Emma, and thank you for the Synopsis organization for this international conference.
Thank you very much. Yeah.
It's our pleasure.
So, next presenter is Dr. Louisa Hamada from IUTD Colmar, France. And the title of the talk is The New Coding Algorithm Using Li-Fi Signal. Hello, Dr. Louisa. Hello.
Good morning.
Hello, yeah, good morning, Dr. Louisa. Please share your screen with us.
Okay.
Yes, your
Do you
screen is
see my
visible to
screen?
us. Yes,
Okay.
yes.
Good. Do you
Please
see the
open the
documents?
presentation. No. Yes, now it is visible. Yes, you can
Okay.
continue.
Okay. Good morning. I welcome the members of Quantum Physics 2023 conference. I have the honor to participate to this conference as a speaker. My name is Luisa Amada. I have a PhD in computer science, networks and telecommunications from the University of Alsace. Today I will talk about the LiFi technology and the new coding algorithm using LiFi signal. LiFi or light fidelity is based on visible light communications using light emitting diode to set up a wireless system entirely in networks. It is about waves included between 3090 and 780 nanometers represented in this picture. So the 3090 is represented by the blue color, and 700 is represented by the red color. Uh, the internet speed is in light using light fidelity system. The internet speed is incredibly high, and the user has everything in few minutes. For the LiFi system, compared with the radio frequency technologies, the transmission is much higher than wireless radio. For the implementation of an LiFi system, three components are included: the transmitter, the VLC transmitter which represented by the light emitting diode, which use the visible light waves to send the data on a wireless communication channel. The second part is the receiver, represented by the photodiode, which transforms the light signal to an electric signal. And we have the canal propagation. We distinguish two kind of propagation: the non-light of sight propagation and the light of sight propagation. So the problem we posed is how to send a message confidentially through the leafy signal and the correct transmission errors while guaranteeing a secure aspect. The idea is to use the Berry-Massey algorithm for the generation of a pseudo-random case whose algorithm has been modified by adding a degree of security. Thank you for listening.
Thank you, Dr. Louisa, for your presentation. So, any
Thank you for your
questions?
optimism.
Okay, no questions then. Thank you once again for your presence and part,
Thank you for the
presentation.
opportunity.
Sorry.
Thank
Yep.
you.
So our next presenter is Dr. Antonieta Marques Caldeira Zebo from University Vale do Paraíba, Brazil. And the title of the talk is Growth Analysis of Panthrophis guttatus in Biotherium Breeding with Phototherapy Treatment. And we have after that one more presentation from him, that is eyelid transcutaneous domestic animals review. Hello, Dr. Antonieta. Hello. Hello, Dr. Antonieta.
Hi, I will be presenting on her behalf.
Oh, okay. So you are the presenter now. Please click on the share icon that you have on the screen. That is the third icon.
Could you put me as presenter?
Okay, sure.
Thank you.
Yes, you are the presenter now. Yes. We can able to see your screen. Please start presenting.
One
Kindly
second.
make it a full screen.
Yes, I will do that. 1 second.
Hmm.
Did it change to full screen?
Yes, it has changed. Yes.
Thank you. Is it still showing? Okay. Good morning, good afternoon, everybody. I will be presenting on behalf of Antonieta. The phototherapy through transdermal ELIB is shown as an option for improvement of systemic organism condition of snakes in captivity. So in order to optimize weight gain of the species, we objectively studied the Penteropis guttatus to analyze the growth through measures of weight and length by applying transdermal ELIB and by standardizing their feeding protocol. So the hypothesis to be answered is to understand whether the technique mentioned before would influence the metabolism of the snakes that were irradiated in a way that they would increase the conversion of their alimentation. So the study was approved by the ethics committee, and the snakes were submitted through a biometric evaluation for 5 months prior to the study, and it was made every 15 days. There were 3 groups with 6 animals. So the group 1, it was restrained animals and no irradiation. The group 2, it was restrained animals with irradiation. And the group 3 was the control group with no restraint nor irradiation. So during the ELIB irradiation, the probe was positioned on the 10th scale, counting from the cloaca where the peripheral vein is located, as you can see on image 1. The procedure was performed for 4 consecutive days for 5 minutes each animal in groups 1 and 2. It was observed their behavior and monitored their heart rate with a Doppler to check its oscillation. There was no disturbance noticed in their organism. However, the growth of this species in captivity can lead to a less efficient organic metabolism, which reflects in a lower food utilization and a lower development. A tendency for greater average gain for mass and length can be seen in irradiated group. However, the ANOVA test performed for each parameter revealed the absence of a statistically significant difference between the groups at 5%. So in conclusion, the influence of transcutaneous ELIB therapy on the growth of experimental snakes was not verified in the present experiment, suggesting the need for application for a longer period to observe an effective difference. So that's it. If you guys have any questions, I'll be here and try to answer. Are there any questions?
Yeah, thank you. Thank you, Dr. Marina, for your presentation. So will you present the another talk as well?
Yes, I'll be presenting the next 2
Okay, sure. You
posters
can
again.
continue with that.
Okay, 1 second. Right now, I'll be presenting another article from Dr. Antonietta. It is about elliptic transcutaneous in domestic animals. It's a review. So among the laser therapies applied to animals, a transcutaneous elliptic therapy is a practice that is extrapolated from human protocols. The objective of this review is to verify that there is in the literature on the application of modified elliptic therapy in animal diseases. The review developed was qualitative and descriptive, with a search for articles available in PubMed and Google Scholar databases over a period of 10 years, with descriptors veterinary medicine, animals, ELIB, intravascular, percutaneous laser. The inclusion criteria were only studies that address the main theme in the treatment of diseases in animals. Among the different applications of light in the animal organism, transcutaneous elliptic therapy is a photobiomodulation technique that has been applied in the treatment of animals with the objective of obtaining the same benefits that it promotes in the human body. The results of this review proposal revealed that there are no studies that demonstrate the use of this therapy in the treatment of pathologies that affect the animals themselves. The unavailability of data regarding the conditions of application of transcutaneous ELIP in animals is highlighted, such as extravascular bed for more suitable therapy, time required for exposure of blood flow, volume of circulating blood, thickness of the stratum corneum, in order to guarantee the efficient delivery and absorption of light energy in the animal's body to obtain the benefits of ELIP, so similarly to what happens in the human body. However, it is essential that the veterinarian understands the physical properties of the laser to define the correct dosage, the light parameters, and in this way guarantee the therapeutic effectiveness of this therapy in different pathologies of the different animals and species treated. So this way we can conclude that there is a lack of recognized scientific studies on the use of elliptic therapy in animals and shows that the need to validate the technique in different animal species. So if you guys have any questions.
Yes, thank you, Dr. Marina, for this presentation. You have one more presentation left, that is the use of phototherapy in the treatment of lesion caused by habronema in equid. Yeah, please continue with this presentation.
Thank you. So now I'll be presenting about the use of phototherapy in the treatment of lesion caused by Abronema species in an equid. I'm presenting also in behalf of other authors such as Ellen and Antonietta. Um, so cutaneous abronemosis is characterized by difficulty to heal inflammatory wounds that present exuberating granulomatous tissues in the skin, mucous membranes, and genitalia of liquids. Its etiological agents are Abronema species that are nematodes, whose vectors are flies. The present case report demonstrates the phototherapy effectiveness as an alternative treatment for this pathology in cases of recurrence and drug resistance. The animal was a horse, male, castrated, a mixed breed, 12 years old, that was treated in São José dos Campos, Brazil, presented recurrent lesion of cutaneous aponeuromyoses in the labial commissure region. The initial treatment was a systemic therapy with ivermectin and pyrantel pamoate every 7 days for 30 days, and a local curative with ointment manipulated with ivermectin, dexamethasone, enrofloxacin, and zinc, which was not successful in the lesion regression and its healing process was not established. Therefore, it was recommended one session every 72 hours, totalizing 10 sessions of a treatment with a 660 nanometers laser diode uh, with 6 joules of energy associated with a 470 nanometers LED light with 48 joules of energy. The animal showed a significant improvement in the initial lesion, the initial sessions with laser therapy and complete tissues healing afterwards. The infection of abronymiasis has a predisposing environmental factors that the open manure and high temperatures, since the vector has a higher proliferation levels under these conditions. Also, poor epithelial healing due to different causes and resistance to antiparasitic drugs contribute to the maintenance of this parasite. So in consequence of the wound scarring, the animal's condition and the failure of the pharmacotherapy initially recommended, the treatment with phototherapy was chosen to stimulate the epithelial cells' metabolism, modulate the inflammatory process, and activate the tissue repair cascade. This way, to accelerate the healing process when closing the wound, besides recovering the animal's health, there is a rupture of the nematode's biological cycle and incidence control of the parasitosis. So, I would like to thank you, all the authors that I was talking in behalf. So Milena, Tiago, Antonieta, and Univapi also for allowing me to work on these studies. So thank you so much. If there are any questions.
Thank you, Dr. Marina, for your presentations. So, any questions from anyone? Okay, no questions then. Thank you once again for your presence and presentation.
Thank you.
Thank you. So this comes to end of our 2 days of conference, and simultaneously we are successfully completed the live conference is going on in Paris, France. We have been fortunate to have a great identities from academics, industries, and other areas with us. We will be glad and thankful if you could join us in our next conference in person or virtually. The dates will be informed to you by email. Also, would request you to provide or share your valuable opinion or feedback with us. For any further queries, you can mail to the concerned program manager. Certificate will be emailed to you. Thank you and have a nice day.